In the vast darkness of space, pinpricks of light shimmer across the cosmic canvas. Stars, those magnificent nuclear furnaces, have long been considered the essential beacons of life in our universe. But what if I told you that life might exist in the most unexpected corners of the cosmos, even in the eternal darkness beyond the warming embrace of any star? When we think about life, we instinctively imagine sunlight streaming through leaves, warming the soil and energizing the intricate dance of biology. From the tiniest microbes to the most complex organisms like ourselves, Earth's biosphere pulses with energy, ultimately derived from our sun. This relationship seems so fundamental that we've made it the cornerstone of our search for life beyond Earth. Find a star like our sun, look for a planet at the right distance, and perhaps you'll find life. But nature has a way of surprising us. The more we explore our own planet, the more we discover life thriving in environments we once thought impossible. Organisms that defy our expectations and force us to reconsider what's possible. Deep beneath the Antarctic ice sheets, in the crushing depths of our oceans, within scalding hot springs, and even in clouds of acid, life finds a way. These extremophiles, as scientists call them, don't just survive in these harsh conditions. They've evolved to require them. Some microbes flourish in temperatures approaching boiling water, while others metabolize sulfur or even radioactive compounds. These discoveries have revolutionized our understanding of life's boundaries, and by extension, where we might find it elsewhere in the universe. So let's embark on a thought experiment. What if life could exist without the warm glow of a star? What environments might harbor biology beyond the reach of stellar radiation? And what might such life look like? Stars provide three essential ingredients for life as we know it: energy, light, and heat. The energy drives complex chemical reactions, the light enables photosynthesis, and the heat maintains temperatures where liquid water, the universal solvent of biology, can exist. A star also acts as a gravitational anchor, holding planets in stable orbits where conditions might remain favorable for billions of years. But are these conditions truly irreplaceable? Or have we simply become too fixated on finding worlds that mirror our own? Consider for a moment the sheer vastness of space. Our Milky Way galaxy alone contains between 100 billion and 400 billion stars, and astronomers estimate there are at least 100 billion galaxies in the observable universe. Those numbers suggest a universe teeming with stars, but the spaces between them, the inky blackness that makes up most of our cosmos, might harbor secrets of their own. Astronomers now believe that our galaxy contains billions of planets that have been ejected from their home systems, wandering the void without a parent star. These rogue planets, once thought to be cosmic anomalies, might actually outnumber the planets orbiting stars. Could these starless wanderers host life in some form? Or consider the moons of our own solar system: Europa circling Jupiter, Enceladus orbiting Saturn, and Titan with its methane lakes. None receive enough sunlight to sustain Earth-like photosynthesis, yet scientists consider them among the most promising places to find extraterrestrial life. Why? Because beneath their icy crusts likely lie vast oceans kept liquid not by the distant sun, but by the gravitational tugging of their parent planets and neighboring moons. The pull of Jupiter stretches and squeezes Europa as it orbits, generating internal heat through friction, a process called tidal heating. This energy could power hydrothermal vents on Europa's ocean floor, creating environments strikingly similar to those where life may have first emerged on Earth. Similar processes occur on Enceladus, where the Cassini spacecraft detected organic molecules erupting from cracks in its icy surface. This realization marks a profound shift in how we think about habitable environments. If life can exist in darkness, powered by geothermal energy rather than sunlight, then the potential habitats for biology expand dramatically beyond the traditional Goldilocks zone around stars. But what about environments even more extreme? Could life exist in the vast emptiness between stars, in the cold void between galaxies, or in the superheated plasma around black holes? These questions once belonged exclusively to science fiction, but advances in our understanding of extremophiles and astrobiology have brought them into the realm of serious scientific inquiry. Some researchers have even proposed forms of life based on entirely different chemical foundations than our own. While all known life uses carbon as its fundamental building block, silicon can form similar complex molecules and might serve as an alternative basis for biology under the right conditions. Other exotic possibilities include life forms based on ammonia instead of water, or organisms that metabolize directly from magnetic fields or radiation. The universe is not only stranger than we imagine, it's stranger than we can imagine. And as we push the boundaries of our understanding, we must be willing to consider possibilities that challenge our most basic assumptions about life. As Carl Sagan once noted, the universe is not required to be in perfect harmony with human ambition. Perhaps life itself is far more versatile and opportunistic than we've dared to dream. By exploring environments beyond the warming glow of stars, we might discover not only new habitats for life, but new definitions of life itself. Our journey into this possibility begins with understanding why stars have been considered so crucial to life. Their immense nuclear furnaces convert hydrogen into helium, releasing astonishing amounts of energy in the process. Every second, our sun converts over 600 million tons of hydrogen into helium, generating enough energy to power human civilization for millions of years. This steady output has warmed Earth's surface for over 4 billion years, creating a remarkably stable environment where complex life could evolve. Stars' bosones also generate the heavier elements necessary for life. Except for hydrogen and helium, products of the Big Bang, every atom in your body was forged in the heart of a star or during its explosive death. The carbon in your DNA, the oxygen you breathe, the calcium in your bones, all were created through stellar nucleosynthesis and then scattered across space when ancient stars exploded as supernovae. We are, quite literally, made of stardust. This deep connection between stars and life makes it tempting to assume that one cannot exist without the other. Yet, as we'll explore, there may be pathways to life that don't depend on the direct nurturing presence of a star, only on the elements and energy previously created by stars throughout cosmic history. Consider that even on Earth, not all ecosystems depend directly on sunlight. In the abyssal depths of our oceans, kilometers below the surface where no sunlight penetrates, rich communities of organisms thrive around hydrothermal vents. These black smokers emit superheated water laden with minerals and chemicals that would be toxic to surface dwellers, but provide energy for specialized bacteria through chemosynthesis, a process analogous to photosynthesis, but powered by chemical reactions rather than light. These bacteria form the foundation of complex food webs that include bizarre creatures like giant tube worms, eyeless shrimp, and ghost white crabs. Entire ecosystems divorced from the sun's energy. If such communities can flourish in Earth's deep oceans, could similar biospheres exist in the subsurface oceans of icy moons throughout our solar system and beyond? The possibility becomes even more intriguing when we consider that these deep-sea ecosystems might better represent Earth's earliest life forms than those dependent on photosynthesis. Many scientists believe that life on Earth may have originated around such hydrothermal vents, only later adapting to use the abundant energy from sunlight as photosynthesis evolved. If life began in darkness before reaching toward the light, then perhaps darkness is not as hostile to biology as we might assume. Indeed, the first living organisms on Earth likely never saw the sun at all, thriving instead in the chemical-rich environments of the early ocean floor. This realization has profound implications for our search for extraterrestrial life. If biology can emerge and sustain itself without direct stellar energy, then habitable environments might be far more common than we've assumed. The universe might be teeming with life in places we've barely begun to consider. Dark oceans beneath ice crusts, subsurface regions of rogue planets, or environments powered by exotic energy sources we're only beginning to understand. When we look at the night sky, we see only a fraction of what's really out there. Between the stars lie vast stretches of seemingly empty space, cosmic deserts that we've long assumed to be barren of life. But what if these interstellar regions harbor their own unique forms of biology, adapted to conditions we can barely imagine? The concept of life without stars challenges not just our understanding of biology, but our very conception of what it means to be alive. On Earth, life is defined by its ability to metabolize energy, respond to stimuli, reproduce, and evolve. These functions require energy and a medium for complex chemistry, traditionally thought to be liquid water. But could other substances serve similar roles in environments vastly different from Earth's? Scientists have speculated about the possibility of organisms based on liquid methane or ammonia rather than water, particularly in the cold regions of outer planets and their moons. Saturn's moon Titan, for instance, has lakes of liquid methane and ethane, where some researchers have suggested that methane-based life might exist, using the abundant hydrocarbons as both solvent and energy source. The temperature ranges where these alternative biochemistries might function are far removed from the comfortable warmth of Earth's sunlit surfaces. Life in liquid methane would operate at temperatures around -180 degrees Celsius, conditions that would instantly freeze water solid, but where methane flows as freely as water does on Earth. Similarly, life based on ammonia would function at temperatures around -33 degrees Celsius. While frigid by Earth standards, such temperatures are quite common throughout the outer solar system and beyond, where the warming influence of our sun barely reaches. But temperature is just one aspect of habitability. Life also requires energy to drive its metabolic processes. Without a star's radiation, what energy sources might power biology in the darkness of space? Potential alternatives include radioactive decay, which generates heat inside planets and moons, tidal heating from gravitational interactions, chemical energy from redox reactions, and even the subtle influx of cosmic rays that permeates all of space. While individually, these energy sources might seem insufficient compared to the flood of solar radiation Earth receives, they persist for billions of years, and in combination, might sustain simple forms of life. Radioactive decay, in particular, has played a crucial role in Earth's history, helping to maintain our planet's internal heat long after its formation. The natural decay of radioactive elements like uranium, thorium, and potassium in Earth's crust and mantle generates heat that drives plate tectonics and volcanic activity. Similar processes likely occur within other planetary bodies, potentially creating subsurface environments where life could emerge. Scientists have even discovered microorganisms on Earth that can harness the energy from radioactive decay directly. In the depths of a gold mine in South Africa, researchers found bacteria that use radioactive uranium to power their metabolism, essentially eating radiation. If such adaptations evolved on our own planet, might similar or even more exotic strategies emerge elsewhere? Tidal heating provides another star-independent energy source. As we've already seen with Europa and Enceladus, the gravitational pull from a massive planet or moon can physically stretch and compress smaller bodies as they orbit, generating friction and heat. This process can maintain liquid water oceans beneath icy crusts for billions of years without any input from stellar radiation. The energy available from tidal heating can be substantial. In the case of Io, Jupiter's innermost large moon, tidal forces generate enough heat to make it the most volcanically active body in our solar system. While Io's surface is too extreme for life as we know it, the principle demonstrates how powerful this energy source can be. Even in the vast emptiness between stars, cosmic rays, high-energy particles accelerated by distant supernovae and other cataclysmic events permeate space. Though sparse by terrestrial standards, these particles carry enormous energy and, over time, could power simple metabolic processes in specialized organisms. The cold, dark regions between stars also contain complex organic molecules formed through interactions between cosmic rays and interstellar dust. Astronomers have detected amino acids, the building blocks of proteins, in meteorites and interstellar clouds, suggesting that the precursors to life might form even in the absence of stars. This brings us to perhaps the most fascinating possibility: life existing not on or within planets at all, but in the near vacuum of interstellar space itself. While such an environment seems impossibly hostile, some scientists have proposed that complex molecular structures might form and even reproduce in the tenuous clouds of gas and dust that drift between stars. These structures would bear little resemblance to Earth life, perhaps existing as intricate patterns of charged particles or as vast, diffuse networks spanning thousands of kilometers. They would metabolize incredibly slowly by our standards, perhaps taking centuries or millennia to complete processes that Earth organisms accomplish in seconds. But in the timeless expanse of cosmic evolution, even such glacial biochemistry might eventually give rise to complexity. If this sounds like science fiction, it's worth remembering that many scientific discoveries began as speculative ideas far removed from conventional thinking. The notion of bacteria thriving in boiling hot springs or feeding on radioactive waste would have seemed absurd to biologists a century ago. Yet we now know both occur naturally on Earth. As our understanding of life's fundamental requirements expands, so too does our conception of where it might exist. The traditional view places stars at the center of habitability, with life restricted to planets orbiting at just the right distance. But a broader perspective suggests a cosmos rich with potential habitats, from the icy moons of gas giants to wandering planets between stars, from the diffuse clouds of interstellar space to the energetic regions around black holes. This expansive view of life's possibilities doesn't diminish the importance of stars. Indeed, stars remain essential to the universe's ability to generate and distribute the elements needed for complex chemistry. Without the nuclear forges of stars creating heavy elements and the explosive power of supernovae scattering them across space, the building blocks of life would remain locked in simple hydrogen and helium. But once these elements exist, once the cosmos has been seeded with carbon, nitrogen, oxygen, and other essentials, perhaps the ongoing presence of a star becomes optional rather than mandatory. Perhaps life, in its endless adaptability, can find ways to thrive even in the darkness between stars. This thought experiment forces us to confront our most basic assumptions about what makes a world habitable. It challenges us to imagine life not as a rare and delicate phenomenon requiring perfect conditions, but as a robust and opportunistic process that emerges wherever energy flows and complex chemistry is possible. The implications extend beyond pure scientific curiosity. If life can exist without stars, the potential habitats in our universe multiply exponentially. The search for extraterrestrial life would need to expand far beyond sun-like stars and their planets, to include the vast interstellar regions that make up most of our galaxy. Such a shift in perspective might also inform our understanding of life's origins on Earth. Did the first living things emerge in sunlit pools, as traditionally imagined, or in the darkness of deep-sea vents? Was our planet's early ocean floor more representative of the universe's typical habitable environments than its sunlit surface? These questions remind us that our perspective remains limited by our experience. We evolved on a sunlit world, surrounded by life adapted to harvest solar energy. Our biology, our technology, and even our imagination have been shaped by this environment. Stepping beyond these limitations requires a conscious effort to question our most fundamental assumptions. As we prepare to delve deeper into the specifics of potential starless habitats, let's keep in mind that our exploration is both scientific and philosophical. We're probing not just the conditions under which biology might function, but the very definition of life itself. We're contemplating not just where organisms might exist, but what forms they might take in environments radically different from our own. The cosmos has had billions of years to experiment with chemistry and energy flows across an unimaginable variety of conditions. Given time and opportunity, the fundamental drive toward complexity that we observe in living systems might manifest in ways we have yet to imagine. Before we speculate further on these exotic possibilities, let's take a closer look at exactly why stars have been so crucial to the emergence and sustenance of life on Earth. Understanding the specific roles that our Sun plays in Earth's biosphere will help us identify which functions might be replaced by alternative energy sources and which might truly be indispensable. This examination will provide the foundation for our journey into environments where life might thrive without a star to call its own. Our sun rises each morning in a spectacle of light and warmth that has defined life on Earth for billions of years. This daily miracle, so common that we often take it for granted, represents one of the most fundamental relationships in our biosphere, the dependence of nearly all living things on stellar energy. To understand whether life could exist without stars, we must first comprehend the profound ways in which stars like our sun nurture and sustain life. At its core, our sun is an enormous nuclear fusion reactor, converting approximately 600 million tons of hydrogen into helium every second. This reaction releases energy in the form of photons, particles of light, that travel outward from the sun's core, eventually reaching Earth after a journey of about 8 minutes. This continuous stream of energy powers nearly every ecosystem on our planet, either directly through photosynthesis or indirectly through food webs that ultimately depend on photosynthetic organisms. The process of photosynthesis itself stands as one of the most remarkable chemical reactions in nature. Plants, algae, and certain bacteria capture photons from sunlight and use that energy to convert carbon dioxide and water into glucose and oxygen. This seemingly simple reaction, powered by packets of stellar energy, forms the foundation of Earth's biosphere. Without it, our planet would host only the simplest microbial ecosystems, huddling around alternative energy sources like hydrothermal vents or radioactive minerals. The oxygen we breathe, the very molecule that enables our high-energy metabolism, is a byproduct of photosynthesis. Before photosynthetic bacteria evolved around 3 billion years ago, Earth's atmosphere contained almost no free oxygen. The subsequent rise in atmospheric oxygen, known as the Great Oxygenation Event, transformed our planet's chemistry and paved the way for complex multicellular life. Every breath we take connects us to ancient cyanobacteria that first harnessed stellar energy to split water molecules and release oxygen. But the sun provides more than just energy for photosynthesis. Its steady radiation maintains Earth's surface temperature within a range where liquid water, the universal solvent of known biology, can exist. Water's unique properties make it ideal for life. It dissolves many substances, facilitates chemical reactions, transports nutrients, and buffers temperature changes. The fact that water remains liquid across a relatively wide temperature range, from 0 to 100 degrees Celsius at Earth's surface pressure, provides a stable environment for complex biological processes. This temperature stability exists because Earth orbits at just the right distance from the Sun, within what astronomers call the habitable zone, or Goldilocks zone. Too close to our star, and water would vaporize into steam. Too far, and it would freeze solid. The narrow band where water remains predominantly liquid allows for the rich tapestry of marine and terrestrial ecosystems that characterize our living planet. Stars also play a crucial role in planetary formation and composition. As stellar nurseries, vast clouds of gas and dust collapse under gravity to form new stars. The remaining material often coalesces into planets. The composition of these planets depends on their distance from the forming star, with rocky worlds like Earth developing in the inner regions where lighter elements have been blown away by stellar radiation and winds. This sorting process creates planets with diverse compositions, from the gas giants of the outer solar system to the rocky worlds of the inner regions. The heavy elements that make up Earth, iron, silicon, oxygen, and others, were forged in previous generations of stars and then incorporated into our solar system as it formed. Without this stellar processing of elements, planets suitable for life as we know it could not exist. Beyond providing energy and creating habitable worlds, stars serve as gravitational anchors that maintain stable planetary orbits. Earth's nearly circular path around the Sun, with only minor variations over millions of years, provides the climatic stability needed for complex life to evolve. More erratic orbits might subject a planet to extreme temperature fluctuations, making it difficult for advanced life forms to develop. The Sun's gravity also helps protect Earth from the hazards of interstellar space. Jupiter and the other gas giants, locked in their own stable orbits by solar gravity, act as cosmic shields. Their immense gravitational fields deflecting or capturing many comets and asteroids that might otherwise impact Earth. While impacts have occurred throughout our planet's history, sometimes with catastrophic consequences for existing life forms, they would likely be far more frequent without this protective arrangement. Stars even influence planetary magnetic fields, which provide crucial protection from cosmic radiation. Earth's magnetic field, generated by the motion of molten iron in our planet's core, shields the surface from the solar wind, a stream of charged particles constantly emitted by the Sun. Without this magnetic protection, the solar wind would gradually strip away Earth's atmosphere, as likely happened to Mars when its core cooled and its magnetic field weakened. The relationship between stars and life extends to biological rhythms as well. The alternation of day and night, driven by Earth's rotation relative to the Sun, has profoundly shaped the evolution of life. Most organisms have developed circadian rhythms, internal biological clocks synchronized with this daily cycle. From sleep patterns to feeding behaviors, from photosynthetic activity to migration timing, countless biological processes are calibrated to the predictable rhythm of sunlight and darkness. Seasonal changes, caused by Earth's axial tilt as it orbits the Sun, add another layer of temporal structure to life's activities. Flowering plants bloom in spring, animals migrate or hibernate in response to changing light and temperature, and ecosystems pulse with activity cycles tied to these stellar-driven seasons. These predictable patterns have allowed for the evolution of complex ecological relationships and life history strategies that maximize survival in a changing but cyclical environment. Even our own biology bears the imprint of our relationship with the Sun. Human skin produces vitamin D when exposed to sunlight, a crucial adaptation that ensures we obtain this essential nutrient. Our eyes evolved to detect precisely the wavelengths of light that penetrate Earth's atmosphere, the visible spectrum emitted abundantly by our yellow dwarf star. Our waking and sleeping cycles, hormone production, and metabolic processes all show adaptations to the day-night cycle imposed by our relationship with the Sun. The Sun's influence extends even to our psychology and culture. Light has positive associations in nearly every human society, linked with knowledge, safety, and enlightenment. Darkness, by contrast, often symbolizes ignorance, danger, or uncertainty. Our languages, religions, and mythologies frequently incorporate solar imagery, from the sun gods of ancient Egypt and Greece to modern metaphors about bright ideas or sunny dispositions. These cultural patterns reflect our species' fundamental dependence on stellar energy and illumination. Given these profound connections between stars and life, it's little wonder that astrobiologists have focused their search for extraterrestrial life on planets orbiting stars similar to our Sun. The traditional concept of habitability assumes that life elsewhere would require similar conditions to Earth: stable stellar energy input, liquid water, and a rocky planetary surface. This perspective has guided our exploration of exoplanets, worlds orbiting stars beyond our solar system. Since the first confirmed discovery in 1995, astronomers have identified thousands of exoplanets, with particular interest in those within their stars' habitable zones. Missions like the Kepler Space Telescope and the Transiting Exoplanet Survey satellite have revolutionized our understanding of planetary systems, revealing that planets are common throughout the galaxy. Yet as we survey these distant worlds, we must remember that our search criteria reflect our Earth-centric perspective. We look for planets at distances from their stars where water could remain liquid, assuming that photosynthesis or similar processes would form the basis of any potential biosphere. But what if these assumptions limit our imagination? What if life can adapt to conditions far different from those we consider habitable? Recent discoveries within our own solar system have begun to challenge these traditional views. The icy moons Europa and Enceladus likely harbor subsurface oceans kept liquid by tidal heating rather than direct solar warming. These vast water reservoirs might contain more liquid water than all of Earth's oceans combined, despite receiving only a fraction of the solar energy that reaches our planet. Similarly, Saturn's moon Titan, with its lakes and rivers of liquid methane and ethane, presents an environment where chemical reactions could potentially support exotic forms of life. While Titan receives minimal sunlight, its complex atmospheric chemistry and abundant hydrocarbons provide alternative ingredients for potential biological processes. Even Venus, often dismissed as inhospitable due to its crushing surface pressure and scorching temperatures, might harbor life in the more temperate cloud layers of its upper atmosphere. Recent detections of phosphine, a gas typically produced by biological processes on Earth, have raised intriguing, if controversial, possibilities about microbial life surviving in what we once considered a sterile environment. These examples remind us that life, even within our solar system, might not be limited to the narrow Earth-like conditions we initially imagined. As we expand our search beyond our solar neighborhood, we should keep this diversity of potential habitats in mind. But what about environments even more removed from stellar influence? Could life exist in the vast spaces between stars, on rogue planets drifting through interstellar darkness, or in other light-deprived environments? To answer this question, we must examine whether alternatives exist for each of the critical functions that stars provide for life on Earth. The first and most obvious challenge is energy. Without stellar radiation, what energy sources could power biological processes? Several possibilities exist, each with its own potential and limitations. Geothermal energy, generated by radioactive decay within a planet's core, provides a steady, long-lasting heat source, independent of any star. On Earth, this internal heat drives plate tectonics, volcanic activity, and hydrothermal systems where some microbial life thrives without photosynthesis. A sufficiently massive rogue planet could retain significant internal heat for billions of years, potentially sustaining subsurface ecosystems similar to those in Earth's deep crust or ocean floor. Tidal heating, as we've already discussed in relation to Europa and Enceladus, offers another stellar-independent energy source. While traditionally associated with moons orbiting planets, similar effects could occur in binary planet systems or planets orbiting brown dwarfs, objects too small to sustain hydrogen fusion but larger than gas giants. These gravitational interactions could maintain liquid water or other solvents necessary for complex chemistry. Chemical energy from redox reactions provides yet another possibility. On Earth, chemosynthetic bacteria extract energy from chemical imbalances, using compounds like hydrogen sulfide, methane, or ferrous iron as electron donors. Similar processes could theoretically support simple ecosystems on worlds far from any star, provided the necessary chemical gradients exist. Radioactive decay could directly power biological processes, as demonstrated by certain Earth bacteria that can harness radiation for metabolism. In environments rich in naturally occurring radioactive elements, organisms might evolve to capture the energy released during decay, similar to how plants capture photons during photosynthesis. Even cosmic rays, high-energy particles from distant stellar explosions and other cosmic events, permeate all of space and could, in theory, provide energy for specialized organisms adapted to harness their power. While the energy flux from cosmic rays is far lower than that from direct starlight, it exists everywhere in the universe and could potentially support extremely slow or efficient metabolic processes. Beyond energy, stars provide other benefits that would need alternatives in starless environments. The gravitational stability that stars offer planetary systems might be replaced by mutual gravitational interactions in binary or multiple planet systems, or by planets orbiting other massive objects like black holes or neutron stars. Protection from interstellar hazards might come from a planet's own magnetic field, which could persist without a nearby star if the planet retains a molten, conductive core. Atmospheres could be retained by sufficiently massive worlds, even without the pressure of stellar wind to contain them. The rhythms imposed by day-night cycles and seasons would obviously be absent in starless environments, but biological clocks might instead synchronize with other cyclical phenomena, such as the orbital periods of nearby planets or moons, variations in cosmic ray intensity, or internal planetary processes. Perhaps most significantly, the absence of photosynthesis would require alternative primary production methods to support complex ecosystems. Chemical energy from geothermal sources might support food webs similar to those around Earth's deep-sea vents, where chemosynthetic bacteria form the foundation for communities that include complex multicellular organisms. The question of water or other suitable solvents remains crucial. Without stellar heating, maintaining liquid water requires alternative heat sources. Subsurface oceans, warmed by internal planetary heat or tidal forces, offer the most promising environments, protected from the freezing vacuum of space by kilometers of ice or rock. Such oceans might remain liquid for billions of years, providing stable environments where life could potentially emerge and evolve. For worlds without internal or tidal heating, exotic solvents with much lower freezing points could potentially serve similar roles to water. Liquid methane, ethane, or nitrogen might support chemical reactions and transport processes analogous to those that occur in water-based systems, albeit at much lower temperatures and with different molecular dynamics. Can we imagine what life in these starless environments might look like? Any such speculation must balance scientific principles with creative thinking, as we have no examples beyond Earth to guide us. Nevertheless, we can make educated guesses based on the constraints and opportunities these environments would present. Life in subsurface oceans would likely be microscopic, at least initially, with simple single-celled organisms extracting energy from chemical gradients near hydrothermal vents or other geologically active regions. Without photosynthesis, these environments would contain much less energy than Earth's sunlit biosphere, potentially limiting the size and complexity of organisms that could evolve. However, given sufficient time and stable conditions, more complex life forms might emerge. We see hints of this potential in Earth's deep-sea vent communities, where bacteria support ecosystems that include tube worms, crustaceans, and specialized fish, all existing without direct solar energy. While these ecosystems ultimately depend on oxygen produced by surface photosynthesis, they demonstrate that complex life can adapt to light-deprived environments. Life based on alternative chemistries would likely appear even more alien to our eyes. Organisms in the methane lakes of worlds like Titan might use different cellular structures, metabolic pathways, and information storage molecules than Earth life. They might operate at much slower rates due to the lower temperatures, with lifespans and reproductive cycles measured in centuries rather than days or years. Radiation-powered organisms in interstellar space might exist as vast, diffuse structures, perhaps colony-like aggregations of simple units spread across kilometers, maximizing their surface area to capture sparse energy. Their metabolism might operate at rates thousands or millions of times slower than Earth life, with evolutionary changes occurring over timescales that dwarf the entire history of life on our planet. Would such organisms develop intelligence? Could consciousness emerge in these exotic environments? These questions venture beyond current scientific understanding into realms where philosophy and speculation dominate. Intelligence on Earth evolved in response to specific environmental pressures and opportunities, shaped by predator-prey relationships, environmental changes, and social dynamics. Different selective pressures in starless environments would likely produce very different forms of cognition, if they produced it at all. One might argue that environments with less available energy would favor intelligence as an adaptation, allowing organisms to make more efficient use of limited resources. Alternatively, the stability of subsurface oceans, protected from external disturbances like impacts, solar flares, or climate changes, might reduce the selective pressure for adaptability that helped drive the evolution of intelligence on Earth. Regardless of the specific forms it might take, Life in starless environments would represent a profound expansion of our understanding of biology's possibilities. It would demonstrate that life is not merely a fragile phenomenon dependent on perfect conditions, but a robust process that can emerge wherever energy flows through complex chemical systems. This perspective has profound implications for our search for extraterrestrial life. If biology can exist without stars, then habitable environments might be far more common than we've assumed. The space between stars, previously considered barren from a biological perspective, might host its own unique forms of life. Rogue planets, ejected from their home systems and wandering the galaxy, could carry subsurface ecosystems through the darkness of interstellar space. Even within our own solar system, this broader conception of habitability expands the environments we should investigate. Beyond the traditional focus on Mars, with its potential for subsurface water and relatively Earth-like conditions, we should explore the subsurface oceans of Europa and Enceladus, the hydrocarbon lakes of Titan, and perhaps even the cloud layers of gas giants like Jupiter and Saturn. As we continue our exploration of the cosmos, keeping an open mind about the potential diversity of life will be crucial. The universe has had billions of years to experiment with chemistry and energy flows across an unimaginable variety of conditions. Our search for life beyond Earth should reflect this potential diversity, looking not just for familiar biosignatures, but for any indication of chemical or energy patterns that deviate from abiotic expectations. But is sunlight truly irreplaceable? While stars provide abundant energy through radiation, we've seen that alternative sources exist: geothermal heat, tidal forces, chemical gradients, radioactive decay, and cosmic rays. None of these alternatives matches the intensity of direct starlight, but they persist over billions of years and in combination might sustain simple or highly efficient forms of life. The real question may not be whether life can exist without stars, but what kinds of complexity it might achieve in their absence. Without the abundant energy of photosynthesis, could starless life evolve beyond microbial forms? Could it develop multicellularity, mobility, intelligence? The answers remain speculative, but the possibilities challenge us to expand our conception of life's potential. Imagine a world shrouded in perpetual ice, its surface a gleaming shell of frozen water stretching horizon to horizon. Above, the stars shine with unfiltered brilliance in an airless sky, their light reflecting off crystalline plains that have remained solid for billions of years. This frozen wasteland seems utterly hostile to life, a dead world locked in an eternal winter. Yet beneath this icy armor lies a secret: vast oceans of liquid water, warmed not by the distant sun, but by forces from within. These hidden seas might harbor some of the most promising environments for extraterrestrial life in our solar system. This isn't science fiction. It's a scientific model of several moons orbiting the gas giants of our outer solar system. Worlds like Europa circling Jupiter, or Enceladus, and Titan in orbit around Saturn. These icy satellites represent a class of worlds entirely different from the rocky planets of the inner solar system, and they challenge our Earth-centric notions of where life might exist. Europa, the smallest of Jupiter's 4 Galilean moons, serves as the prototype for these ice-covered ocean worlds. Slightly smaller than Earth's moon, Europa's smooth surface is crisscrossed by a network of cracks and ridges, features that hint at the dynamic processes occurring beneath. Images from spacecraft like Galileo reveal few impact craters, suggesting that the surface ice is relatively young and constantly being renewed. This renewal could only occur if Europa's icy shell floats atop a liquid layer that allows for movement and restructuring of the surface. What keeps this ocean liquid, so far from the sun's warming rays? The answer lies in Europa's relationship with Jupiter and its fellow moons. As Europa orbits Jupiter, the gravitational pulls of the massive planet and the other Galilean satellites, Io, Ganymede, and Callisto, tug at it from different directions. These competing forces stretch and squeeze Europa, creating friction that generates heat in its interior, a process known as tidal heating. This internal heat melts the ice from below, maintaining a global subsurface ocean that scientists believe may contain twice as much water as all of Earth's oceans combined. Sandwiched between the ice shell above and a rocky mantle below, this liquid realm remains insulated from the extreme cold of space, potentially providing a stable environment where life could evolve. Europa isn't alone in this category. Saturn's moon Enceladus, despite its small size, just 500 kilometers in diameter, has provided some of the most compelling evidence for habitable environments beyond Earth. In 2005, the Cassini spacecraft discovered spectacular geysers erupting from Enceladus's south polar region, spewing water vapor and ice particles hundreds of kilometers into space. Subsequent analysis of these plumes revealed they contain organic compounds, nitrogen-bearing molecules, and indicators of hydrothermal activity, all key ingredients for life as we know it. What makes this discovery particularly exciting is that these materials originate from the subsurface ocean, providing a direct sample of this potentially habitable environment without the need to drill through kilometers of ice. Like Europa, Enceladus maintains its liquid ocean through tidal heating, though the specific mechanisms differ due to its smaller size and different orbital characteristics. The concentration of geysers at the South Pole suggests that the ice shell is thinner in this region, possibly just a few kilometers thick compared to the estimated 15 to 25 kilometers on Europa. Both Europa and Enceladus likely feature rocky seafloors where water interacts directly with mineral-rich surfaces, creating chemical gradients that could power biological processes. On Earth, similar environments exist at hydrothermal vents, fissures in our planet's seafloor where geologically heated water erupts into the cold ocean. These vents support rich ecosystems based not on photosynthesis, but on chemosynthesis, where microorganisms derive energy from chemical reactions involving hydrogen sulfide, methane, and other compounds. The discovery of these black smoker ecosystems in Earth's deep oceans in the late 1970s revolutionized our understanding of life's requirements. Prior to this, scientists assumed that all complex ecosystems ultimately depended on photosynthesis and, by extension, sunlight. The thriving communities around hydrothermal vents, including giant tube worms, unique crustaceans, and specialized microbes, demonstrated that life could exist entirely independent of solar energy, using chemical energy from Earth's interior instead. This realization dramatically expanded the potential habitats for life throughout the universe. If complex ecosystems can thrive in perpetual darkness using geochemical energy, then sunlight, and by extension, proximity to a star, may not be essential for life. The subsurface oceans of icy moons suddenly became prime candidates in the search for extraterrestrial life. What might life in these subsurface oceans look like? Without light, photosynthesis as we know it would be impossible. Instead, organisms would likely rely on chemosynthesis, extracting energy from chemical disequilibria at the boundary between the ocean and the rocky core. Just as Earth's hydrothermal vent ecosystems are based on microbes that oxidize hydrogen sulfide and other reduced compounds, European or Enceladian life might metabolize chemicals produced by water rock interactions at their respective ocean floors. Such ecosystems would likely be dominated by microbial life, single-celled organisms adapted to extract energy from specific chemical reactions. These microbes might form mats or colonies around energy sources, such as hydrothermal vents or regions where particular minerals are exposed to the ocean water. In Earth's deep biosphere, we find microorganisms surviving on remarkably little energy, reproducing very slowly, but persisting in stable communities for thousands or millions of years. Similar adaptations might evolve in the resource-limited environments of subsurface alien oceans. Could more complex life evolve in these environments? Earth's hydrothermal vent ecosystems suggest that multicellular organisms can indeed thrive in chemosynthesis-based food webs. However, these Earth examples still benefit from oxygen produced by photosynthetic organisms elsewhere in the ocean. Without photosynthesis to generate oxygen, alien ocean ecosystems might remain at a microbial level of complexity, or they might evolve entirely different metabolic strategies unknown on Earth. In thinking about potential life in these subsurface oceans, we must consider not just the presence of liquid water and energy sources, but also the availability of essential elements and compounds. Carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, sometimes abbreviated as HNOPS, form the backbone of Earth life. Are these elements available in the subsurface oceans of icy moons? Evidence suggests they are. The plumes of Enceladus contain organic compounds, including various hydrocarbons and complex carbon-nitrogen molecules. Spectroscopic analysis of Europa's surface ice reveals the presence of various salts and organic materials, likely representing components of the ocean below that have been brought to the surface through geological processes. The rocky cores of these moons presumably contain a wide range of minerals, similar to those found in Earth's crust and mantle, providing sources for phosphorus, sulfur, and various metals important for biological processes. Time is another crucial factor for the evolution of life. Complex life on Earth took billions of years to develop, requiring stable conditions over immense timescales. Do the subsurface oceans of icy moons offer this kind of stability? Current models suggest they do. The process of tidal heating that maintains these liquid oceans can continue as long as the orbital resonances that drive it remain stable. For Europa and Enceladus, these conditions have likely persisted for much of the solar system's 4.5 billion year history. While there may have been variations in ocean temperature, chemistry, and ice shell thickness over time, the fundamental conditions, liquid water in contact with a mineral-rich rocky substrate, have probably remained consistent for eons, providing ample time for life to potentially emerge and evolve. The ice shells themselves, while initially seeming like barriers, might actually benefit potential ecosystems by providing protection from cosmic radiation and meteorite impacts. Earth's biosphere is shielded from harmful radiation by our magnetic field and atmosphere, but icy moons generally lack these protective features. The thick ice crusts serve as effective radiation shields, creating stable environments where delicate biochemistry could proceed undisturbed. However, this protection comes at a cost: isolation. If life exists in these subsurface oceans, it would have evolved in complete separation from the surface. Unlike Earth, where materials and energy flow between the deep ocean, shallow seas, land, and atmosphere in complex cycles, the ecosystems of ice-covered moons would be largely closed systems, with energy and materials cycling within the ocean or between the ocean and rocky core. This isolation raises fascinating questions about the potential diversity and evolutionary pathways of life in such environments. Would alien ocean life develop extraordinary specialization to exploit limited niches? Or would it evolve remarkable versatility to take advantage of whatever resources become available, without the driving force of photosynthesis to power diverse food webs? Would these ecosystems be simpler than Earth's? Or might they develop equally complex but fundamentally different ecological structures? Our understanding of these questions remains theoretical, based on models and extrapolations from Earth's deep biosphere and hydrothermal ecosystems. To truly understand the potential for life in subsurface oceans, we need direct exploration, missions that can penetrate the ice shells and sample the waters below. Such missions face enormous technical challenges. The ice crusts of Europa and Enceladus are many kilometers thick, requiring drilling or melting technologies far beyond our current capabilities for space missions. Additionally, any mission that breaches these ice shells must adhere to planetary protection protocols, ensuring that Earth microbes don't contaminate pristine alien environments or potentially confuse our search for indigenous life. Despite these challenges, space agencies are developing missions to further investigate these intriguing worlds. NASA's Europa Clipper mission, scheduled to launch in the mid-2020s, will conduct detailed reconnaissance of Europa using ice-penetrating radar to map the thickness of the ice shell and identify potential thin spots or subsurface water pockets. The European Space Agency's Jupiter Icy Moons Explorer, JUICE, will study Ganymede, Callisto, and Europa, focusing on the geology, composition, and internal structure of these worlds. Future missions might include landers to analyze the surface composition of these moons in detail, or even more ambitious concepts like cryobots, robotic probes designed to melt through the ice and release submersibles into the oceans below. While such missions remain speculative, the rapid advancement of technology and growing scientific interest in these environments make them increasingly feasible for the coming decades. Beyond Europa and Enceladus, other worlds in our solar system may harbor similar subsurface oceans. Jupiter's moons, Ganymede and Callisto, likely contain internal water layers, though their greater distance from Jupiter results in less tidal heating and potentially colder, deeper oceans. Saturn's largest moon, Titan, presents a different case entirely. Its thick atmosphere and surface lakes of liquid methane and ethane make it a unique environment in our solar system, but it may also contain a subsurface water ocean beneath its icy crust. Neptune's moon, Triton, captured from the Kuiper Belt in the distant past, shows signs of geological activity that could indicate subsurface liquid, as does Pluto, the most thoroughly studied dwarf planet in the Kuiper Belt. Even distant Pluto, examined by the New Horizons spacecraft in 2015, exhibited unexpected geological features suggesting internal heat sources sufficient to maintain a subsurface ocean for at least part of its history. The potential prevalence of subsurface oceans throughout our solar system suggests that such environments might be common throughout the universe. If liquid water can exist beneath the surfaces of multiple worlds in our solar system, far from the sun's warming influence, then similar conditions might occur on countless moons, orbiting gas giants around other stars, or even on rogue planets drifting between stars. This realization dramatically expands our conception of the habitable zone, the region around a star where liquid water can exist on a planet's surface. Traditional definitions focus on surface habitability, calculating the range of distances where stellar heating balances atmospheric cooling to maintain temperatures suitable for liquid water. But subsurface habitability, maintained by internal heat sources like radioactive decay and tidal forces, could extend far beyond these limits, perhaps making habitable environments more common than previously thought. What would it mean to discover life in a subsurface ocean, existing without sunlight in the cold outer reaches of our solar system? Beyond the profound philosophical implications of finding a second genesis of life, such a discovery would teach us invaluable lessons about the versatility and adaptability of biological processes. Even Venus, often dismissed as inhospitable due to its crushing surface pressure and scorching temperatures, might harbor life in the more temperate cloud layers of its upper atmosphere. Recent detections of phosphine, a gas typically produced by biological processes on Earth, have raised intriguing, if controversial, possibilities about microbial life surviving in what we once considered a sterile environment. These examples remind us that life, even within our solar system, might not be limited to the narrow Earth-like conditions we initially imagined. As we expand our search beyond our solar neighborhood, we should keep this diversity of potential habitats in mind. But what about environments even more removed from stellar influence? Could life exist in the vast spaces between stars, on rogue planets drifting through interstellar darkness, or in other light-deprived environments? To answer this question, we must examine whether alternatives exist for each of the critical functions that stars provide for life on Earth. The first and most obvious challenge is energy. Without stellar radiation, what energy sources could power biological processes? Several possibilities exist, each with its own potential and limitations. Geothermal energy, generated by radioactive decay within a planet's core, provides a steady, long-lasting heat source, independent of any star. On Earth, this internal heat drives plate tectonics, volcanic activity, and hydrothermal systems where some microbial life thrives without photosynthesis. A sufficiently massive rogue planet could retain significant internal heat for billions of years. potentially sustaining subsurface ecosystems similar to those in Earth's deep crust or ocean floor. Tidal heating, as we've already discussed in relation to Europa and Enceladus, offers another stellar-independent energy source. While traditionally associated with moons orbiting planets, similar effects could occur in binary planet systems or planets orbiting brown dwarfs, objects too small to sustain hydrogen fusion but larger than gas giants. These gravitational interactions could maintain liquid water or other solvents necessary for complex chemistry. Chemical energy from redox reactions provides yet another possibility. On Earth, chemosynthetic bacteria extract energy from chemical imbalances, using compounds like hydrogen sulfide, methane, or ferrous iron as electron donors. Similar processes could theoretically support simple ecosystems on worlds far from any star, provided the necessary chemical gradients exist. Radioactive decay could directly power biological processes, as demonstrated by certain Earth bacteria that can harness radiation for metabolism. In environments rich in naturally occurring radioactive elements, organisms might evolve to capture the energy released during decay, similar to how plants capture photons during photosynthesis. Even cosmic rays, high-energy particles from distant stellar explosions and other cosmic events, permeate all of space and could, in theory, provide energy for specialized organisms adapted to harness their power. While the energy flux from cosmic rays is far lower than that from direct starlight, it exists everywhere in the universe and could potentially support extremely slow or efficient metabolic processes. Beyond energy, stars provide other benefits that would need alternatives in starless environments. The gravitational stability that stars offer planetary systems might be replaced by mutual gravitational interactions in binary or multiple planet systems, or by planets orbiting other massive objects like black holes or neutron stars. Protection from interstellar hazards might come from a planet's own magnetic field, which could persist without a nearby star if the planet retains a molten, conductive core. Atmospheres could be retained by sufficiently massive worlds, even without the pressure of stellar wind to contain them. The rhythms imposed by day-night cycles and seasons would obviously be absent in starless environments, but biological clocks might instead synchronize with other cyclical phenomena, such as the orbital periods of nearby planets or moons, variations in cosmic ray intensity, or internal planetary processes. Perhaps most significantly, the absence of photosynthesis would require alternative primary production methods to support complex ecosystems. Chemical energy from geothermal sources might support food webs similar to those around Earth's deep-sea vents, where chemosynthetic bacteria form the foundation for communities that include complex multicellular organisms. The question of water or other suitable solvents remains crucial. Without stellar heating, maintaining liquid water requires alternative heat sources. Subsurface oceans warmed by internal planetary heat or tidal forces offer the most promising environments, protected from the freezing vacuum of space by kilometers of ice or rock. Such oceans might remain liquid for billions of years, providing stable environments where life could potentially emerge and evolve. For worlds without internal or tidal heating, exotic solvents with much lower freezing points could potentially serve similar roles to water. Liquid methane, ethane, or nitrogen might support chemical reactions and transport processes analogous to those that occur in water-based systems, albeit at much lower temperatures and with different molecular dynamics. Can we imagine what life in these starless environments might look like? Any such speculation must balance scientific principles with creative thinking, as we have no examples beyond Earth to guide us. Nevertheless, we can make educated guesses based on the constraints and opportunities these environments would present. Life in subsurface oceans would likely be microscopic, at least initially, with simple single-celled organisms extracting energy from chemical gradients near hydrothermal vents or other geologically active regions. Without photosynthesis, these environments would contain much less energy than Earth's sunlit biosphere. potentially limiting the size and complexity of organisms that could evolve. However, given sufficient time and stable conditions, more complex life forms might emerge. We see hints of this potential in Earth's deep-sea vent communities, where bacteria support ecosystems that include tube worms, crustaceans, and specialized fish, all existing without direct solar energy. While these ecosystems ultimately depend on oxygen produced by surface photosynthesis, they demonstrate that complex life can adapt to light-deprived environments. Life based on alternative chemistries would likely appear even more alien to our eyes. Organisms in the methane lakes of worlds like Titan might use different cellular structures, metabolic pathways, and information storage molecules than Earth life. They might operate at much slower rates due to the lower temperatures, with lifespans and reproductive cycles measured in centuries rather than days or years. Radiation-powered organisms in interstellar space might exist as vast, diffuse structures, perhaps colony-like aggregations of simple units spread across kilometers, maximizing their surface area to capture sparse energy. Their metabolism might operate at rates thousands or millions of times slower than Earth life, with evolutionary changes occurring over timescales that dwarf the entire history of life on our planet. Would such organisms develop intelligence? Could consciousness emerge in these exotic environments? These questions venture beyond current scientific understanding into realms where philosophy and speculation dominate. Intelligence on Earth evolved in response to specific environmental pressures and opportunities, shaped by predator-prey relationships, environmental changes, and social dynamics. Different selective pressures in starless environments would likely produce very different forms of cognition, if they produced it at all. One might argue that environments with less available energy would favor intelligence as an adaptation, allowing organisms to make more efficient use of limited resources. Alternatively, the stability of subsurface oceans, protected from external disturbances like impacts, solar flares, or climate changes, might reduce the selective pressure for adaptability that helped drive the evolution of intelligence on Earth. Regardless of the specific forms it might take, life in starless environments would represent a profound expansion of our understanding of biology's possibilities. It would demonstrate that life is not merely a fragile phenomenon dependent on perfect conditions, but a robust process that can emerge wherever energy flows through complex chemical systems. This perspective has profound implications for our search for extraterrestrial life. If biology can exist without stars, then habitable environments might be far more common than we've assumed. The space between stars, previously considered barren from a biological perspective, might host its own unique forms of life. Rogue planets, ejected from their home systems and wandering the galaxy, could carry subsurface ecosystems through the darkness of interstellar space. Even within our own solar system, this broader conception of habitability expands the environments we should investigate. Beyond the traditional focus on Mars, with its potential for subsurface water and relatively Earth-like conditions, we should explore the subsurface oceans of Europa and Enceladus, the hydrocarbon lakes of Titan, and perhaps even the cloud layers of gas giants like Jupiter and Saturn. As we continue our exploration of the cosmos, keeping an open mind about the potential diversity of life will be crucial. The universe has had billions of years to experiment with chemistry and energy flows across an unimaginable variety of conditions. Our search for life beyond Earth should reflect this potential diversity, looking not just for familiar biosignatures, but for any indication of chemical or energy patterns that deviate from abiotic expectations. But is sunlight truly irreplaceable? While stars provide abundant energy through radiation, we've seen that alternative sources exist: geothermal heat, tidal forces, chemical gradients, radioactive decay, and cosmic rays. None of these alternatives matches the intensity of direct starlight, but they persist over billions of years and in combination might sustain simple or highly efficient forms of life. The real question may not be whether life can exist without stars, but what kinds of complexity it might achieve in their absence. Without the abundant energy of photosynthesis, could starless life evolve beyond microbial forms? Could it develop multicellularity, mobility, intelligence? The answers remain speculative, but the possibilities challenge us to expand our conception of life's potential. Imagine a world shrouded in perpetual ice, its surface a gleaming shell of frozen water stretching horizon to horizon. Above, the stars shine with unfiltered brilliance in an airless sky, their light reflecting off crystalline plains that have remained solid for billions of years. This frozen wasteland seems utterly hostile to life, a dead world locked in an eternal winter. Yet beneath this icy armor lies a secret, vast oceans of liquid water, warmed not by the distant sun, but by forces from within. These hidden seas might harbor some of the most promising environments for extraterrestrial life in our solar system. This isn't science fiction. It's a scientific model of several moons orbiting the gas giants of our outer solar system. Worlds like Europa circling Jupiter, or Enceladus and Titan in orbit around Saturn. These icy satellites represent a class of worlds entirely different from the rocky planets of the inner solar system, and they challenge our Earth-centric notions of where life might exist. Europa, the smallest of Jupiter's 4 Galilean moons, serves as the prototype for these ice-covered ocean worlds. Slightly smaller than Earth's moon, Europa's smooth surface is crisscrossed by a network of cracks and ridges, features that hint at the dynamic processes occurring beneath. Images from spacecraft like Galileo reveal few impact craters, suggesting that the surface ice is relatively young and constantly being renewed. This renewal could only occur if Europa's icy shell floats atop a liquid layer that allows for movement and restructuring of the surface. What keeps this ocean liquid, so far from the sun's warming rays? The answer lies in Europa's relationship with Jupiter and its fellow moons. As Europa orbits Jupiter, the gravitational pulls of the massive planet and the other Galilean satellites, Io, Ganymede, and Callisto, tug at it from different directions. These competing forces stretch and squeeze Europa, creating friction that generates heat in its interior, a process known as tidal heating. This internal heat melts the ice from below, maintaining a global subsurface ocean that scientists believe may contain twice as much water as all of Earth's oceans combined. Sandwiched between the ice shell above and a rocky mantle below, this liquid realm remains insulated from the extreme cold of space, potentially providing a stable environment where life could evolve. Europa isn't alone in this category. Saturn's moon Enceladus, despite its small size, just 500 kilometers in diameter, has provided some of the most compelling evidence for habitable environments beyond Earth. In 2005, the Cassini spacecraft discovered spectacular geysers erupting from Enceladus's south polar region, spewing water vapor and ice particles hundreds of kilometers into space. Subsequent analysis of these plumes revealed they contain organic compounds, nitrogen-bearing molecules, and indicators of hydrothermal activity, all key ingredients for life as we know it. What makes this discovery particularly exciting is that these materials originate from the subsurface ocean, providing a direct sample of this potentially habitable environment without the need to drill through kilometers of ice. Like Europa, Enceladus maintains its liquid ocean through tidal heating, though the specific mechanisms differ due to its smaller size and different orbital characteristics. The concentration of geysers at the South Pole suggests that the ice shell is thinner in this region, possibly just a few kilometers thick compared to the estimated 15 to 25 kilometers on Europa. Both Europa and Enceladus likely feature rocky seafloors where water interacts directly with mineral-rich surfaces, creating chemical gradients that could power biological processes. On Earth, similar environments exist at hydrothermal vents, fissures in our planet's seafloor where geologically heated water erupts into the cold ocean. These vents support rich ecosystems based not on photosynthesis, but on chemosynthesis, where microorganisms derive energy from chemical reactions involving hydrogen sulfide, methane, and other compounds. The discovery of these black smoker ecosystems in Earth's deep oceans in the late 1970s revolutionized our understanding of life's requirements. Prior to this, scientists assumed that all complex ecosystems ultimately depended on photosynthesis and, by extension, sunlight. The thriving communities around hydrothermal vents, including giant tube worms, unique crustaceans, and specialized microbes, demonstrated that life could exist entirely independent of solar energy, using chemical energy from Earth's interior instead. This realization dramatically expanded the potential habitats for life throughout the universe. If complex ecosystems can thrive in perpetual darkness using geochemical energy, then sunlight, and by extension, proximity to a star, may not be essential for life. The subsurface oceans of icy moons suddenly became prime candidates in the search for extraterrestrial life. What might life in these subsurface oceans look like? Without light, photosynthesis as we know it would be impossible. Instead, organisms would likely rely on chemosynthesis, extracting energy from chemical disequilibria at the boundary between the ocean and the rocky core. Just as Earth's hydrothermal vent ecosystems are based on microbes that oxidize hydrogen sulfide and other reduced compounds, Europan or Enceladian life might metabolize chemicals produced by water-rock interactions at their respective ocean floors. Such ecosystems would likely be dominated by microbial life, single-celled organisms adapted to extract energy from specific chemical reactions. These microbes might form mats or colonies around energy sources, such as hydrothermal vents or regions where particular minerals are exposed to the ocean water. In Earth's deep biosphere, we find microorganisms surviving on remarkably little energy, reproducing very slowly but persisting in stable communities for thousands or millions of years. Similar adaptations might evolve in the resource-limited environments of subsurface alien oceans. Could more complex life evolve in these environments? Earth's hydrothermal vent ecosystems suggest that multicellular organisms can indeed thrive in chemosynthesis-based food webs. However, these Earth examples still benefit from oxygen produced by photosynthetic organisms elsewhere in the ocean. Without photosynthesis to generate oxygen, alien ocean ecosystems might remain at a microbial level of complexity, or they might evolve entirely different metabolic strategies unknown on Earth. In thinking about potential life in these subsurface oceans, we must consider not just the presence of liquid water and energy sources, but also the availability of essential elements and compounds. Carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, sometimes abbreviated as THNOPS, form the backbone of Earth life. Are these elements available in the subsurface oceans of icy moons? Evidence suggests they are. The plumes of Enceladus contain organic compounds, including various hydrocarbons and complex carbon-nitrogen molecules. Spectroscopic analysis of Europa's surface ice reveals the presence of various salts and organic materials, likely representing components of the ocean below that have been brought to the surface through geological processes. The rocky cores of these moons presumably contain a wide range of minerals similar to those found in Earth's crust and mantle, providing sources for phosphorus, sulfur, and various metals important for biological processes. Time is another crucial factor for the evolution of life. Complex life on Earth took billions of years to develop, requiring stable conditions over immense timescales. Do the subsurface oceans of icy moons offer this kind of stability? Current models suggest they do. The process of tidal heating that maintains these liquid oceans can continue as long as the orbital resonances that drive it remain stable. For Europa and Enceladus, these conditions have likely persisted for much of the solar system's 4.5 billion year history. While there may have been variations in ocean temperature, chemistry, and ice shell thickness over time, the fundamental conditions, liquid water in contact with a mineral-rich rocky substrate, have probably remained consistent for eons, providing ample time for life to potentially emerge and evolve. The ice shells themselves, while initially seeming like barriers, might actually benefit potential ecosystems by providing protection from cosmic radiation and meteorite impacts. Earth's biosphere is shielded from harmful radiation by our magnetic field and atmosphere, but icy moons generally lack these protective features. The thick ice crusts serve as effective radiation shields, creating stable environments where delicate biochemistry could proceed undisturbed. However, this protection comes at a cost: isolation. If life exists in these subsurface oceans, it would have evolved in complete separation from the surface. Unlike Earth, where materials and energy flow between the deep ocean, shallow seas, land, and atmosphere in complex cycles, the ecosystems of ice-covered moons would be largely closed systems, with energy and materials cycling within the ocean or between the ocean and rocky core. This isolation raises fascinating questions about the potential diversity and evolutionary pathways of life in such environments. Would alien ocean life develop extraordinary specialization to exploit limited niches? Or would it evolve remarkable versatility to take advantage of whatever resources become available without the driving force of photosynthesis to power diverse food webs? Would these ecosystems be simpler than Earth's? Or might they develop equally complex but fundamentally different ecological structures? Our understanding of these questions remains theoretical, based on models and extrapolations from Earth's deep biosphere and hydrothermal ecosystems. To truly understand the potential for life in subsurface oceans, we need direct exploration, missions that can penetrate the ice shelves and sample the waters below. Such missions face enormous technical challenges. The ice crusts of Europa and Enceladus are many kilometers thick, requiring drilling or melting technologies far beyond our current capabilities for space missions. Additionally, any mission that breaches these ice shelves must adhere to planetary protection protocols, ensuring that Earth microbes don't contaminate pristine alien environments or potentially confuse our search for indigenous life. Despite these challenges, space agencies are developing missions to further investigate these intriguing worlds. NASA's Europa Clipper mission, scheduled to launch in the mid-2020s, will conduct detailed reconnaissance of Europa, using ice-penetrating radar to map the thickness of the ice shell and identify potential thin spots or subsurface water pockets. The European Space Agency's Jupiter Icy Moons Explorer, JUICE, will study Ganymede, Callisto, and Europa, focusing on the geology, composition, and internal structure of these worlds. Future missions might include landers to analyze the surface composition of these moons in detail, or even more ambitious concepts like cryobots, robotic probes designed to melt through the ice and release submersibles into the oceans below. While such missions remain speculative, the rapid advancement of technology and growing scientific interest in these environments make them increasingly feasible for the coming decades. Beyond Europa and Enceladus, other worlds in our solar system may harbor similar subsurface oceans. Jupiter's moons, Ganymede and Callisto, likely contain internal water layers, though their greater distance from Jupiter results in less tidal heating and potentially colder, deeper oceans. Saturn's largest moon, Titan, presents a different case entirely. Its thick atmosphere and surface lakes of liquid methane and ethane make it a unique environment in our solar system, but it may also contain a subsurface water ocean beneath its icy crust. Neptune's moon, Triton, captured from the Kuiper Belt in the distant past, shows signs of geological activity that could indicate subsurface liquid, as does Pluto, the most thoroughly studied dwarf planet in the Kuiper Belt. Even distant Pluto, examined by the New Horizons spacecraft in 2015, exhibited unexpected geological features, suggesting internal heat sources sufficient to maintain a subsurface ocean for at least part of its history. The potential prevalence of subsurface oceans throughout our solar system suggests that such environments might be common throughout the universe. If liquid water can exist beneath the surfaces of multiple worlds in our solar system, far from the sun's warming influence, then similar conditions might occur on countless moons, orbiting gas giants around other stars, or even on rogue planets drifting between stars. This realization dramatically expands our conception of the habitable zone. the region around a star where liquid water can exist on a planet's surface. Traditional definitions focus on surface habitability, calculating the range of distances where stellar heating balances atmospheric cooling to maintain temperatures suitable for liquid water. But subsurface habitability, maintained by internal heat sources like radioactive decay and tidal forces, could extend far beyond these limits, perhaps making habitable environments more common than previously thought. What would it mean to discover life in a subsurface ocean, existing without sunlight in the cold outer reaches of our solar system? Beyond the profound philosophical implications of finding a second genesis of life, such a discovery would teach us invaluable lessons about the versatility and adaptability of biological processes. Life in these environments would likely use fundamentally different strategies than most Earth organisms. Without photosynthesis to capture light energy and produce oxygen, their biochemistry might rely on alternative electron donors and acceptors, different metabolic pathways, and perhaps even different bases for information storage and replication. Studying such alien biochemistry could reveal new principles of molecular organization, energy management, and evolutionary adaptation. Even if this life shared common ancestry with Earth life, transported between worlds by meteorites in a process called panspermia, its long isolation and adaptation to radically different conditions would likely have produced unique evolutionary innovations. Comparing these adaptations to Earth life could help us understand which features of biology are universal constraints and which are contingent outcomes of Earth's specific conditions. Beyond the scientific insights, finding life in subsurface oceans would transform our perspective on humanity's place in the cosmos. If life can emerge and thrive in such seemingly hostile environments, in perpetual darkness far from the sun, then the universe might be far more conducive to life than we've traditionally assumed. We might inhabit not a rare oasis of life in a largely sterile cosmos, but one expression of a phenomenon that manifests wherever the basic ingredients, water, energy, and organic chemistry, come together for sufficient time. The exploration of subsurface oceans represents one of the most promising frontiers in astrobiology, the search for environments that might harbor life beyond Earth. Unlike the arid surface of Mars or the searing heat of Venus, these hidden oceans offer conditions remarkably similar to environments where life thrives on Earth. Liquid water, stable temperatures, and energy sources independent of direct sunlight. As we develop the technologies to explore these mysterious realms, we prepare to answer one of humanity's most profound questions. Are we alone in the universe? The answer may lie not on the surface of distant exoplanets circling other stars, but much closer to home, beneath the icy crusts of worlds in our own solar system. If we do find life in these subsurface oceans, it would demonstrate that life can indeed thrive without direct stellar energy, existing in darkness but sustained by the internal heat of worlds. Such a discovery would suggest that life might be far more common throughout the cosmos than we have imagined, existing not just on planets within the narrow habitable zones around stars, but in the subsurface environments of countless icy worlds orbiting gas giants, brown dwarfs, or even wandering starless through interstellar space. The ice-covered moons of our outer solar system thus offer us more than scientific curiosity. They provide a test case for a revolutionary idea that life's domain extends far beyond the sun-warmed surfaces of Earth-like planets. In exploring these frozen worlds, we're not just searching for extraterrestrial life, we're redefining our understanding of where life can exist throughout the universe. But what about worlds that don't orbit any star at all? Could life exist on planets that wander the interstellar void, far from the warming influence of stellar radiation? To answer this question, we must venture even further from our sun-centered perspective, into the darkness between the stars, where rogue planets drift in eternal night. In the vast emptiness between stars, far from the warming rays of any sun, drift some of the most mysterious objects in our galaxy, rogue planets. These orphaned worlds, untethered to any star, wander the interstellar void in perpetual darkness. Once considered rare cosmic anomalies, Astronomers now believe these nomadic planets may number in the trillions in our galaxy alone, potentially outnumbering the stars themselves. Could these starless wanderers, adrift in the coldest reaches of space, possibly harbor life? The very concept challenges our sun-centered understanding of habitability. Without stellar warmth, the surface of a rogue planet would freeze to temperatures approaching the cosmic background, a frigid -270 degrees Celsius. At first glance, such worlds seem utterly inhospitable to life. But as we've seen, with the ice-covered moons of our outer solar system, surface conditions don't always tell the complete story. To understand the potential for life on rogue planets, we must look beneath their frozen exteriors to the dynamic processes that might occur within. Rogue planets begin their existence like any other planet, forming within the protoplanetary disk around a young star. But unlike their more fortunate siblings, these worlds become ejected from their birth systems through gravitational interactions with other planets or passing stars. The ejection process itself is violent, flinging the planet into interstellar space at velocities that can reach tens of kilometers per second relative to its original star. Once ejected, a rogue planet carries with it whatever atmosphere, surface features, and internal heat it possessed at the moment of its departure. Larger planets, particularly gas giants similar to Jupiter or Neptune, would retain substantial internal heat from their formation, heat generated by gravitational contraction and radioactive decay of elements in their cores. This internal warmth, though gradually diminishing over time, could persist for billions of years. For smaller, rocky worlds similar to Earth, the picture is more complex. Their smaller mass means less gravitational energy during formation and faster cooling rates over time. However, radioactive decay of elements like uranium, thorium, and potassium within their mantles would continue to generate heat long after ejection from their parent star. Earth itself derives about half its internal heat from radioactive decay, heat that drives plate tectonics and maintains our planet's magnetic field. A rogue Earth-like planet would experience dramatically different surface conditions after ejection. Without solar heating, its oceans would freeze solid, and its atmosphere might condense or escape to space. But beneath this frozen shell, geothermal heat could potentially maintain a layer of liquid water, a subsurface ocean similar to those suspected to exist within Europa or Enceladus. The thickness of the ice crust would depend on the planet's internal heat production and the insulating properties of the ice itself. Models suggest that a rogue Earth-like planet with similar internal heat production to our own might maintain a global subsurface ocean beneath an ice shell several to tens of kilometers thick. This ocean, sandwiched between ice above and rock below, could remain liquid for billions of years, time enough for life to potentially emerge and evolve. The concept isn't purely theoretical. Evidence suggests that our own solar system may harbor planets in its distant outskirts that receive so little solar energy that they function essentially as rogue planets. Astronomers have identified several distant objects in the Kuiper Belt, and beyond that appear unexpectedly warm for their distance from the Sun, suggesting internal heat sources similar to those that would operate in true rogue planets. Gas giant rogue planets offer even more intriguing possibilities. Jupiter-sized worlds ejected into interstellar space would retain tremendous internal heat, potentially enough to keep any moons they carried with them habitable through tidal heating. Imagine a system like Jupiter and Europa cast adrift between the stars. The massive planet's gravitational pull would continue to need its moon, generating friction and heat to maintain a subsurface ocean regardless of the absence of stellar warmth. This scenario creates the remarkable possibility of habitable moons orbiting rogue planets, oases of potential life drifting through the cosmic darkness. Such systems would be entirely self-contained, deriving all their energy from gravitational interactions and radioactive decay, rather than external stellar radiation. But could life emerge on a rogue planet that formed that way from the beginning? Or must life already exist before a planet becomes a rogue? The answer depends on whether the basic ingredients for life and sufficient energy sources exist on these wandering worlds. Most rogue planets would carry with them whatever volatile compounds, water, methane, ammonia, and other organic molecules they accumulated during formation. Gas giants in particular would retain thick atmospheres rich in hydrogen and helium, with deeper layers containing water, ammonia, and methane ices. Rocky rogue planets might carry substantial water reserves in their mantles and crusts, just as Earth does. The energy required for life could come from several sources. Geothermal heat from radioactive decay would provide a steady, long-lasting energy source. For larger planets or moons experiencing tidal heating, gravitational energy converted to heat could power hydrothermal systems at the boundary between rocky cores and subsurface oceans. Chemical energy from redox reactions between water and minerals could support chemosynthetic organisms, similar to those found in Earth's deep biosphere. Recent research suggests another fascinating possibility: hydrogen-based ecosystems. As water interacts with certain minerals deep within a planet's crust, the process of serpentinization can produce hydrogen gas, a potential energy source for microorganisms. On Earth, we've discovered entire ecosystems based on hydrogen metabolizing bacteria in deep crustal environments, suggesting similar processes could support life within rogue planets. The potential for life on or within rogue planets raises profound questions about how we search for habitable environments beyond our solar system. The traditional habitable zone concept, defining habitability based on a planet's distance from its star, becomes inadequate when considering worlds that generate their own heat internally rather than relying on stellar radiation. This expanded conception of habitability suggests that the universe might contain far more potential abodes for life than previously thought. If rogue planets can maintain subsurface oceans and energy sources sufficient for biology, then habitable environments might exist not just around stars, but throughout the vast interstellar spaces between them. The challenge, of course, lies in detecting and studying these nomadic worlds. Without a star to orbit, rogue planets don't produce the periodic dimming of starlight that astronomers use to identify exoplanets via the transit method. Nor do they create the subtle gravitational wobbles in a parent star that enable detection via the radial velocity technique. Instead, astronomers must rely on direct imaging, capturing the faint thermal glow from the planet itself. This approach works best for young, massive rogue planets that still retain significant heat from their formation, making them glow dimly in infrared wavelengths. Several candidate rogue planets have been identified this way, including objects with masses a few times that of Jupiter. Smaller, Earth-sized rogue planets remain mostly beyond our current detection capabilities, though future telescopes like the Nancy Grace Roman Space Telescope may be able to spot them through gravitational microlensing, a technique that detects planets when they briefly magnify the light from background stars. If rogue planets are indeed as common as recent estimates suggest, perhaps hundreds of billions or even trillions in our galaxy alone, they would constitute a vast and largely unexplored category of potentially habitable environments. Their prevalence would transform our understanding of where life might exist in the universe, extending the domain of habitability far beyond the traditional star-centered view. The life that might evolve in or on these wandering worlds would face unique challenges and opportunities. Without a stable day-night cycle or seasons to provide temporal structure, organisms would need to develop different rhythms or operate without the cyclical patterns that have shaped Earth life. Without photosynthesis to capture stellar energy, alternative metabolic strategies would predominate, perhaps based on chemosynthesis, hydrogen metabolism, or energy sources we've yet to discover. The isolation of a rogue planet, drifting alone through interstellar space, separated from other worlds by vast distances, would create a closed ecosystem where materials would cycle internally with minimal external inputs. Evolution in such an environment might favor extreme efficiency in resource utilization and energy conservation, with organisms adapting to extract maximum benefit from limited resources. But rogue planets aren't necessarily doomed to eternal isolation. As they drift through the galaxy, these wandering worlds would occasionally pass near star systems, potentially close enough for gravitational interactions. Some might even be captured into new stellar orbits, transitioning from rogues to conventional planets. During these close encounters, material exchange through impacts or gravitational disturbances could transport organic compounds or even microorganisms between worlds, potentially seeding life from one system to another. This possibility connects to the theory of panspermia, the idea that life might spread between worlds via meteorites or other mechanisms. Rogue planets could serve as both carriers and recipients in this process, picking up microorganisms during close encounters with other planetary systems and transporting them across interstellar distances. Over the billions of years of galactic evolution, such exchanges might have occurred countless times, potentially creating a network of biologically connected worlds throughout the galaxy. The concept of habitable rogue planets challenges us to reconsider our assumptions about where life might exist in the universe. The default image of habitability, a rocky planet orbiting at just the right distance from a sun-like star, represents just one possible environment among many. The dark, frozen surfaces of rogue planets might conceal subsurface environments as capable of supporting life as the sunlit surface of Earth, albeit through very different mechanisms. This expanded view of habitability has practical implications for our search for life beyond Earth. If rogue planets can support subsurface biospheres, then similar environments might exist throughout our own solar system and beyond. The techniques and technologies we develop to identify biosignatures in these environments could inform how we search for life on distant exoplanets and their moons. Consider a hypothetical rogue planet with Earth-like composition ejected from its star system early in its history. Its surface would quickly freeze as it departed the warming influence of its star, forming a thick shell of ice that would insulate the interior. Internal heat from radioactive decay would maintain temperatures sufficient to keep water liquid at certain depths, creating a boundary where ice transitions to liquid water. At this boundary, energy flows, both thermal and chemical, would create conditions potentially suitable for life. Minerals dissolved from the rocky mantle would provide necessary elements: carbon, nitrogen, phosphorus, sulfur, and various metals, while the overlying ice would protect from cosmic radiation and impacts. The liquid water environment would offer a medium for chemical reactions and material transport, much as Earth's oceans do. Life in such an environment would likely be microbial, at least initially, with organisms adapted to extract energy from chemical gradients rather than light. These microbes might metabolize hydrogen produced through water-rock interactions, or use metal ions as electron donors and acceptors in energy-yielding reactions. Communities might form around hotspots of hydrothermal activity, where energy and nutrient availability would be highest. Could more complex life evolve in these conditions? The answer depends on the energy available and the stability of the environment over time. Earth's complex multicellular life required not just liquid water and basic nutrients, but abundant energy from photosynthesis to drive the formation of oxygen-rich environments. Without this photosynthetic foundation, subsurface ecosystems on rogue planets might remain primarily microbial, as most of Earth's deep biosphere does. However, alternative energy sources might support more complex ecosystems under certain conditions. A particularly massive rogue planet with higher internal heat production could generate more vigorous hydrothermal activity, potentially supporting richer and more diverse communities. A system where a large rogue planet induces tidal heating in orbiting moons might create even more energetic environments, with complex chemical cycles driven by the continuous input of gravitational energy. The time factor is crucial as well. Life on Earth required billions of years to progress from simple single-celled organisms to complex multicellular life forms. Rogue planets, with their stable internal heat sources and protection from external disturbances, could provide the long-term environmental stability necessary for evolutionary experimentation and increasing complexity. In imagining life on rogue planets, we must also consider alternatives to water-based biochemistry. At the extremely low surface temperatures of these wandering worlds, liquid water would exist only deep beneath the frozen crust, but other compounds might remain liquid at much lower temperatures, potentially supporting different forms of chemical organization. Methane, for instance, remains liquid down to -182 degrees Celsius at standard pressure, and even lower under pressure. On a frigid rogue planet, lakes or even oceans of liquid methane might exist closer to the surface than liquid water would. Could complex organic chemistry occur in such environments, potentially leading to lifelike systems based on different solvents than water? Saturn's moon Titan provides a partial analogue within our own solar system. Despite receiving minimal solar heating, Titan maintains lakes and seas of liquid methane and ethane, along with a thick nitrogen-methane atmosphere. Complex organic chemistry occurs in this cold environment, producing a variety of hydrocarbon compounds that rain onto the surface and collect in liquid reservoirs. While we've found no evidence of life on Titan, its organic chemistry demonstrates that complex molecular interactions can occur even at temperatures far below water's freezing point. A rogue planet with Titan-like surface conditions might host similar organic chemistry, potentially developing novel types of organization that fulfill some criteria for life. Such systems would operate at much slower rates than Earth life due to the lower temperatures, with chemical reactions taking hours, days, or longer, instead of the split-second interactions that occur in water at Earth temperatures. Deep beneath the surface, where temperatures rise due to internal heat, more conventional water-based life might exist alongside these exotic surface chemistries. This creates the intriguing possibility of multiple biospheres on a single rogue planet, perhaps methane-based systems near the surface and water-based ecosystems in deeper regions, each adapted to its specific environmental niche. The diversity of potential conditions on rogue planets suggests they might serve as natural laboratories for a wide range of chemical and potentially biological systems. Some might host only the simplest procellular chemistry, others complex microbial ecosystems, and perhaps a few could support more complex life forms adapted to their unique conditions. This spectrum of possibilities expands our conception of habitability beyond the conventional definition focused on surface water and stellar energy. In the absence of a nearby star, life finds other energy sources, other solvents, other rhythms, and patterns of organization. The cosmos becomes not a sparse scattering of sunlit oases in a vast desert, but a diverse landscape of potential habitats, each with its own set of opportunities and constraints for the emergence of complexity. What are the implications of this expanded view of habitability? If life can exist on or within rogue planets, then the number of potentially habitable environments in our galaxy alone could be in the trillions, far exceeding the number of conventional planets orbiting within their stars' habitable zones. Life might be far more common throughout the cosmos than our star-centered perspective suggests, existing in forms and environments we're only beginning to imagine. This possibility doesn't diminish the special nature of Earth-like environments, the sunlit, oxygen-rich, water-abundant worlds that support the kind of complex multicellular life we're familiar with. But it suggests that life itself, in its simpler forms, might be a much more pervasive phenomenon, emerging wherever energy flows through complex chemical systems for sufficient time, regardless of whether those systems orbit a star or drift alone through the interstellar void. As we contemplate the potential for life on rogue planets, we should remember that these worlds exist not as isolated cases, but as part of a continuum of environments within our galaxy, from the scorching surfaces of planets orbiting close to their stars, to the temperate conditions of habitable zone worlds like Earth, to the frozen surfaces, but potentially habitable interiors of distant ice worlds and rogue planets. Each environment offers different possibilities for the emergence and evolution of living systems. The universe has had billions of years to experiment with chemistry and energy flows across this vast range of conditions. Our search for life beyond Earth should reflect this diversity. looking not just for familiar biosignatures in familiar environments, but for the broader patterns that might indicate the presence of organized, self-sustaining systems in environments very different from our own. If rogue planets can indeed support life, then habitability becomes not a rare privilege of perfectly positioned planets around suitable stars, but a common potential of worlds throughout the galaxy. Life, in its fundamental essence, might not be tethered to stars after all, but free to emerge wherever the basic ingredients and energy sources coincide for sufficient time. But there's another path to life, one that doesn't require a sun or a planet. Some scientists propose that life might exist not just on celestial bodies, but between them, in the vast reaches of interstellar space itself. Could microscopic organisms drift through the cosmos, spread by the process of panspermia? To explore this possibility, we must venture beyond conventional planetary environments into the space between the stars, where conditions become even more extreme, but where life, in its endless adaptability, might still find a way to survive. The vast emptiness between stars seems an unlikely place to search for life. In these cold, radiation-filled voids where atoms might travel for years before encountering another particle, the conditions appear utterly hostile to biology. Yet some scientists propose that life might not only survive here, but travel through these cosmic deserts, seeding planets across interstellar distances in a process known as panspermia. Could the space between stars serve not just as a barrier to life, but as its highway through the cosmos? The theory of panspermia, from the Greek words for all and seed, suggests that life might spread between worlds, carried on meteoroids, asteroids, or other planetary fragments ejected into space by impacts or other cataclysmic events. First proposed in its modern form by Swedish chemist Svante Arrhenius in the early 20th century, the concept has evolved from fringe speculation to serious scientific inquiry as our understanding of extremophile organisms and space environments has advanced. For panspermia to be viable, microscopic life forms would need to survive a harrowing journey, violent ejection from their home world, prolonged exposure to the vacuum and radiation of space, and finally a fiery entry into a new planetary atmosphere. Each stage presents formidable challenges that would destroy most organisms. Yet research on Earth's hardiest microbes suggests that some might indeed endure this interplanetary or even interstellar odyssey. The journey begins with ejection from a planetary surface. When a large asteroid or comet strikes a planet, the impact can accelerate surface material to speeds exceeding the planet's escape velocity, launching rocks and debris into space. These ejected materials carry with them whatever microorganisms might have been living on or within them. The force of such impacts subjects these hitchhikers to crushing pressures and intense heat, conditions that would destroy most life forms. Yet studies suggest that some microbes could survive even these extreme forces if protected within cracks or pores in rock. Evidence from our own solar system supports the plausibility of this first step. Meteorites of Martian origin have been discovered on Earth, blasted from the red planet's surface by ancient impacts and eventually captured by Earth's gravity. Analysis of these Martian rocks reveals that they were not subjected to sterilizing temperatures throughout their interiors during ejection, suggesting that any microorganisms within them might have survived the initial launch into space. Once in space, ejected material and any potential biological passengers face a harsh environment characterized by vacuum, extreme temperature fluctuations, and intense radiation. Vacuum exposure can be lethal to most organisms, causing cell membranes to rupture and essential water to boil away. Yet some bacterial spores can enter dormant states where metabolic activity ceases almost entirely, allowing them to survive in vacuum conditions for extended periods. Temperature presents another challenge. In direct sunlight, exposed surfaces in space can heat to well over 100 degrees Celsius, while shadowed regions can plunge to nearly absolute zero. This extreme cycling would stress cellular structures beyond their limits. However, within sufficiently large meteoroids, internal temperatures remain more stable, potentially providing a protected environment for microorganisms embedded deep within porous rock. Perhaps the most serious threat comes from radiation, particularly high-energy cosmic rays and solar ultraviolet radiation, which can shatter DNA and other biological molecules. On Earth, organisms are largely protected from this radiation by our atmosphere and magnetic field. In space, exposure is direct and constant, accumulating damage over time that would eventually render most organisms non-viable. Yet here too, certain microbes show remarkable resilience. The bacterium Deinococcus radiodurans can withstand radiation doses thousands of times higher than would kill a human, thanks to efficient DNA repair mechanisms that can reassemble its shattered genome after extreme radiation damage. While even D. radiodurans would eventually succumb to the radiation encountered during an interstellar journey lasting thousands or millions of years, its remarkable tolerance demonstrates that biological mechanisms can evolve to counter even this most penetrating threat. The final stage of the panspermia process, arrival at a new world, presents perhaps the greatest challenge of all. Entry into a planetary atmosphere subjects a meteoroid to intense friction, heating its exterior to thousands of degrees. For any organisms to survive, they must be sheltered deep enough within the rock to avoid these sterilizing temperatures, yet not so deep that they remain permanently entombed if the meteorite survives to impact the surface. Studies of meteorites that have fallen to Earth show that while their exteriors form a superheated melt crust during atmospheric entry, their interiors often remain remarkably cool. In some cases, organic compounds that would decompose at relatively low temperatures have been found intact within meteorites, suggesting that living organisms might similarly survive the journey if sufficiently protected. Once safely delivered to a new planetary surface, any surviving organisms would face yet another challenge, adapting to an alien environment with potentially very different conditions than their world of origin. They would need to extract energy and nutrients from available sources, reproduce in competition with any native life forms, and establish a viable population before going extinct. A tall order even for the most adaptable microbes. Despite these formidable obstacles, laboratory studies and natural experiments provide intriguing evidence that panspermia might be possible, at least within a planetary system. Experiments aboard the International Space Station have demonstrated that certain bacterial spores and lichens can survive direct exposure to space conditions for years when partially shielded from radiation. These findings suggest that protected within meteoroids, hardier organisms might survive much longer journeys. The discovery of extremophiles on Earth, organisms adapted to conditions once thought incompatible with life, further strengthens the case for possible interplanetary transfer. Microbes thrive in environments ranging from superheated hydrothermal vents to the dry, radiation-bombarded Atacama Desert, from highly acidic mine drainage to alkaline soda lakes, from the crushing pressures of the deep ocean to the near vacuum of the upper atmosphere. This remarkable adaptability suggests that at least some Earth organisms might survive temporary exposure to the even more extreme conditions of space. Within our solar system, the case for panspermia seems plausible enough that some scientists seriously consider whether life on Earth and Mars, if found, might share a common origin through ancient exchange of material. The planets have exchanged an estimated billion tons of rock over their history due to impact events, potentially allowing for biological transfer in either direction. But what about panspermia between star systems, the true interstellar transport of life? Here, the challenge becomes far greater. The distances between stars are measured not in millions of kilometers, but in light years, with even the closest star systems requiring tens of thousands of years to reach at the typical velocities of ejected planetary material. During such extended journeys, accumulating radiation damage would likely sterilize any biological material, even if protected within rocky shelters. However, several scenarios might allow for viable interstellar panspermia despite these challenges. One possibility involves much faster transit times. Some material ejected during supernova explosions or by close stellar encounters might be accelerated to a significant fraction of the speed of light, potentially reducing interstellar transit times to centuries or even decades for nearby star systems. At these timescales, particularly resistant organisms might survive the journey, especially if their dormant states include highly efficient DNA repair mechanisms that can reverse radiation damage once conditions become favorable again. Another possibility involves transpermia, the deliberate transport of microorganisms by technological civilizations. An advanced society might intentionally seed other worlds with life, either as a form of cosmic gardening or to prepare planets for future habitation. While speculative, this scenario bypasses many of the challenges of natural panspermia by allowing for protected transport and targeted delivery. A third, more exotic possibility involves life existing not on or within planetary bodies, but directly in the interstellar medium itself. While the extremely low density of matter in interstellar space makes conventional cell-based life implausible, some scientists have proposed that complex organic molecules might form and interact in the thin clouds of gas and dust that float between stars. These structures would bear little resemblance to Earth life, perhaps existing as vast, diffuse networks spanning thousands of kilometers and metabolizing at rates thousands or millions of times slower than terrestrial organisms. The dense molecular clouds where stars and planets form contain a surprising diversity of organic compounds, including amino acids, nucleobases, and other building blocks of Earth life. These molecules form through reactions driven by cosmic radiation and low-temperature chemistry, gradually increasing in complexity over the millions of years that these clouds persist. Might this natural organic chemistry sometimes cross the threshold into self-replicating systems that we would recognize as alive? Such interstellar organisms, if they exist, would be extremely difficult to detect or study with current technology. Their metabolism would operate on timescales of centuries or millennia rather than seconds or minutes, and their physical structure would be so diffuse as to be nearly indistinguishable from the ambient cloud. Yet they would represent a truly space-dwelling form of life, adapted to the very conditions that seem most hostile to biology as we know it. While such exotic possibilities remain speculative, the more conventional forms of panspermia, the transport of microbial life between planets via meteorites, find support in a growing body of scientific evidence. Experiments have demonstrated the surprising resilience of certain microorganisms to space conditions, and the discovery of Martian meteorites on Earth confirms that planetary materials can indeed travel between worlds. If panspermia occurs regularly within our solar system, it would have profound implications for our search for extraterrestrial life. Mars, Europa, Enceladus, and other potentially habitable environments might not host independent origins of life, but rather outposts of a common biology first established on Earth or another world. Finding life elsewhere in our solar system that shares fundamental biochemical features with Earth life, the same genetic code, similar membrane structures, or common metabolic pathways, would strongly suggest such a shared origin through panspermia. Conversely, discovering life with fundamentally different biochemistry would indicate an independent origin, a second genesis that would definitively prove that life can emerge under a variety of conditions. This finding would have even more profound implications, suggesting that the universe might be teeming with diverse forms of life that emerged independently wherever conditions permitted. The study of panspermia connects to broader questions about life's origins and distribution throughout the cosmos. If microbial transport between worlds is common, then life might have originated once in a particularly favorable environment and subsequently spread to various planets and moons. This process could greatly increase the prevalence of life, allowing it to establish footholds in environments where it might not have emerged independently, but could nonetheless survive once delivered. Evidence for such processes might be found by studying the meteorites that regularly fall to Earth. These cosmic messengers sometimes contain complex organic compounds, including amino acids, the building blocks of proteins. While these compounds form through abiotic chemical processes rather than biological activity, Their presence demonstrates that space itself serves as a natural laboratory for organic chemistry, producing increasingly complex molecules that might, under the right conditions, lead toward life. The Murchison meteorite, which fell in Australia in 1969, contains more than 90 different amino acids, many of which are rare or absent in Earth's biology. These compounds formed in space through reactions involving simpler molecules like hydrogen cyanide, ammonia, and water, all abundant in the interstellar medium. Over millions of years, such processes might generate a vast array of organic compounds, a subset of which could serve as precursors to biological systems. This scenario suggests a cosmic continuum of chemical complexity, with simple molecules in interstellar space gradually combining to form more complex organic compounds. These compounds concentrate in star-forming regions and protoplanetary disks, eventually becoming incorporated into comets, asteroids, and planets. On suitable worlds, this delivered organic material might provide the raw ingredients for life to emerge through further chemical evolution. From this perspective, panspermia represents not just the transport of fully formed life between worlds, but a broader process of distributing chemical complexity throughout the cosmos. The ingredients for life, and perhaps life itself in its simplest forms, might be continually exchanged between planets, moons, and interstellar regions in a grand network of chemical and potentially biological interconnection. Recent discoveries lend credence to this integrated view. Interstellar objects passing through our solar system, like Oumuamua in 2017 and Comet Borisov in 2019, demonstrate that material regularly travels between star systems. While these particular visitors likely spent too long in interstellar space to harbor viable organisms, they illustrate the physical connectivity between seemingly isolated stellar neighborhoods. The potential for life to survive interstellar journeys remains an open scientific question with compelling arguments on both sides. The extreme time spans involved, tens or hundreds of thousands of years even for relatively nearby star systems, present a formidable challenge for any biological system, no matter how resilient. Yet the discovery of ever more extreme adaptations among Earth's microorganisms continues to expand our conception of life's survival limits. Tardigrades, microscopic animals colloquially known as water bears, can enter a state called cryptobiosis when faced with extreme conditions. In this state, their metabolic activity decreases to near zero, and they can survive temperatures from near absolute zero to well above boiling. Radiation doses thousands of times higher than lethal for humans, the vacuum of space, and complete dehydration for decades. While even tardigrades would eventually succumb to the cumulative radiation damage of interstellar transit, their remarkable abilities hint at the potential for even more extreme survival strategies that might evolve elsewhere. To conclusively determine whether interstellar panspermia is viable would require direct experimentation, exposing candidate organisms to simulated interstellar conditions for extended periods, and then testing their viability. Such experiments have begun on modest scales, with microorganisms exposed to space conditions aboard satellites and the International Space Station for months or years. Expanding these trials to decades or centuries would provide more definitive answers but presents obvious practical challenges. In the meantime, the study of extremophiles on Earth continues to yield surprising insights about the boundaries of life's adaptability. Deep in the crust, microbes have been found living in conditions of extreme pressure, temperatures above 120 degrees Celsius, high radiation from radioactive minerals, and near complete isolation from surface energy sources. Some of these organisms divide only once per century or millennium, maintaining minimal metabolic activity that allows them to repair damage and persist in their harsh environments. Such discoveries continually expand our understanding of life's potential to survive in extreme environments, including the possibility of panspermia. Life, it seems, is far more tenacious and adaptable than we once imagined, finding ways to endure conditions that seem utterly hostile to biology. If panspermia is indeed viable across interstellar distances, it would transform our understanding of life's distribution throughout the galaxy. Rather than isolated outposts around individual stars, life might form an interconnected network spanning multiple star systems, with genetic innovations potentially spreading across interstellar spaces over billions of years of cosmic evolution. Under such a scenario, the galaxy might contain not thousands of independent biospheres, but a smaller number of biological families, each descended from a common origin, but diversified through adaptation to local conditions on countless worlds. Finding evidence of such relationships, perhaps through distinctive biochemical signatures shared across star systems, would rank among the most profound scientific discoveries in human history. The concept of panspermia thus offers a third possibility, beyond the traditional binary of life existing only on planets orbiting stars, or not existing at all. Life might indeed require the energy and elements forged by stars and concentrated on planets, but once established, it might spread beyond its birthplace, traveling through the seeming barriers of interstellar space to establish new outposts wherever conditions permit. This more expansive view sees life not as a rare and isolated phenomenon, but as a potentially self-propagating process that, once begun, might extend its reach across vast cosmic distances. The borders between habitable zones would blur, with life's domain expanding through its own tenacity and adaptability, rather than remaining confined to the narrow regions traditionally considered suitable for its emergence. As we continue to explore our solar system and beyond, the possibility of panspermia remains a compelling hypothesis to be tested through both observation and experiment. The answers we find may reveal not just whether life exists elsewhere in the cosmos, but whether all life, wherever found, might share a common ancestry in the grand family tree of cosmic biology. But while panspermia offers a pathway for life to travel between established planetary systems, other environments exist that straddle the boundary between stars and planets. Objects known as brown dwarfs, too large to be planets but too small to sustain the nuclear fusion that powers true stars, present yet another category of potential habitats for life. Environments with unique characteristics that might support exotic biospheres unlike anything familiar from Earth. In the cosmic hierarchy between stars and planets exists an enigmatic class of objects that astronomers call brown dwarfs. Too massive to be considered planets, yet too small to sustain the hydrogen fusion that powers true stars, these celestial nomads occupy a unique position in our understanding of stellar evolution. With masses ranging from about 13 to 75 times that of Jupiter, brown dwarfs represent nature's near misses, objects that almost became stars but fell just short of the ignition threshold. Yet in their failure to become stars, they might offer unexpected opportunities for life to emerge in forms vastly different from what we know on Earth. Brown dwarfs form like stars through the gravitational collapse of gas and dust in molecular clouds, but their lower mass prevents them from achieving the core temperatures and pressures needed to sustain hydrogen fusion. Instead, most brown dwarfs experience only a brief period of deuterium fusion, a heavier isotope of hydrogen with a lower fusion threshold, before settling into a long, slow cooling process that will last for hundreds of billions of years. Despite their name, brown dwarfs don't actually appear brown to the eye. Young brown dwarfs glow a dull red from the heat of their formation and deuterium fusion, gradually shifting to infrared wavelengths as they cool over billions of years. The coolest known brown dwarfs have surface temperatures as low as 225 degrees Celsius, cooler than many household ovens, and vastly cooler than even the smallest true stars, which maintain surface temperatures of at least 2000 degrees Celsius. This relatively cool temperature range makes brown dwarfs intriguing candidates in the search for habitable environments. Unlike stars, which emit most of their energy as visible light, brown dwarfs primarily radiate in the infrared spectrum. This infrared radiation could theoretically warm planets orbiting a brown dwarf, creating temperature conditions where liquid water might exist on their surfaces. The habitable zone around a brown dwarf, the orbital distance where a planet could maintain liquid water, would be extremely close to the brown dwarf itself, perhaps just 1 to 3 million kilometers away. compared to the 150 million kilometers that separate Earth from the Sun. At such close distances, planets would likely become tidally locked, with one side perpetually facing the brown dwarf, while the other remains in permanent darkness. This tidal locking creates a unique environment unlike anything in our solar system. The day side would receive a constant influx of infrared radiation, while the night side would remain in perpetual darkness and cold. Between these extremes, a terminator zone, the boundary between day and night, might maintain temperatures suitable for liquid water and potentially life. The concept of habitable planets around brown dwarfs gained scientific credibility in 2013 when astronomers using the WISE Space Telescope discovered a brown dwarf called WISE 0855 plus 0714, located just over 7 light-years from Earth, making it one of our closest cosmic neighbors. With a surface temperature of around 250 degrees Celsius, this Y-class brown dwarf demonstrated that such cool objects exist in our stellar neighborhood and could potentially host habitable worlds. Planets orbiting brown dwarfs would experience a very different illumination pattern than Earth. Instead of the bright, visible sunlight that powers life on our planet, these worlds would receive primarily infrared radiation, heat energy rather than light. This distinction has profound implications for potential life, as infrared radiation penetrates water more effectively than visible light, but lacks the energy to power photosynthesis as we know it. Without traditional photosynthesis, life on brown dwarf planets would need alternative energy sources. One possibility involves photosynthetic pigments adapted to capture infrared photons, perhaps using multiple lower energy photons to accomplish what single higher energy photons do in Earth's plants. Such adaptive biochemistry isn't merely speculative. Some bacteria on Earth can indeed perform a limited form of infrared photosynthesis, suggesting that more sophisticated versions might evolve in environments where infrared radiation is the primary energy source. Alternatively, life might abandon photosynthesis entirely, relying instead on chemosynthesis or other metabolic strategies that harvest energy from chemical gradients rather than radiation. Such adaptations already exist in Earth's deep subsurface and hydrothermal vent ecosystems, where microorganisms derive energy from redox reactions involving sulfur, iron, hydrogen, and other compounds. The close proximity required for a planet to remain in a brown dwarf's habitable zone creates other unique conditions that would shape potential life. Powerful tidal forces would need these nearby planets, generating internal heat through friction similar to what occurs on Jupiter's moon Io or Saturn's Enceladus. This tidal heating could maintain internal warmth and potentially drive geological activity, even as the brown dwarf itself gradually cools over billions of years. Intense magnetic interactions would likely occur between brown dwarfs and their close orbiting planets as well. Brown dwarfs generate strong magnetic fields, sometimes thousands of times more powerful than Jupiter's already substantial magnetosphere. A planet orbiting within this magnetic environment would experience induced currents, auroral displays, and radiation belts far more intense than anything in our solar system. These conditions might seem hostile to life, but they could also provide energy sources for specially adapted organisms able to harvest electrical potential or metabolize radiation-produced compounds. The planetary systems around brown dwarfs might differ fundamentally from those around stars like our Sun. The reduced heating during system formation would allow volatile compounds, water, ammonia, methane, to condense closer to the central object, potentially creating worlds rich in these life-essential materials, even at close orbital distances. This contrasts with solar systems like ours, where the intense heat of the forming star drove these volatiles outward, creating the stark division between rocky inner planets and gas-rich outer worlds. One intriguing possibility is that brown dwarfs might be particularly well-suited to host what astronomers call water worlds, planets whose mass consists predominantly of water in various forms, from surface oceans to high-pressure ice layers in their interiors. Such planets would offer vast habitable volumes compared to predominantly rocky worlds like Earth. potentially supporting more extensive and diverse biospheres. The lifespans of brown dwarfs introduce another fascinating dimension to their potential habitability. Unlike stars, which exhaust their nuclear fuel and die after millions or billions of years, brown dwarfs cool extremely slowly. Without fusion to power them, they simply radiate away their initial heat over trillions of years, gradually dimming but never experiencing the cataclysmic end that awaits true stars. This extraordinary stability might provide habitable conditions for timescales far longer than possible around normal stars, allowing for extended evolutionary experimentation and adaptation. Consider that Earth has hosted complex life for roughly 500 million years, just a fraction of our Sun's 10 billion-year lifespan. A brown dwarf might maintain habitable conditions for tens or even hundreds of billions of years, offering evolutionary timelines 20 to 200 times longer than Earth's entire history of complex life. What forms of biological complexity might emerge given such expanded evolutionary horizons? The search for planets around brown dwarfs presents significant technological challenges. Their intrinsic dimness makes them difficult to observe, and the small habitable zones mean that potentially habitable planets would orbit very close to their brown dwarfs, making traditional detection methods challenging. Despite these obstacles, astronomers have already confirmed the existence of planets orbiting brown dwarfs, including a system called 2MASS J12073346-3933259b, which hosts a planetary mass companion. As our observational capabilities improve, particularly with the deployment of instruments specifically designed to study infrared bright objects, we can expect to discover more brown dwarf planetary systems. The James Webb Space Telescope, with its unprecedented infrared sensitivity, may provide our first opportunity to characterize the atmospheres of planets orbiting nearby brown dwarfs, potentially revealing signatures of habitability or even life. The prevalence of brown dwarfs in our galaxy remains somewhat uncertain, but current estimates suggest they may be extraordinarily common, perhaps nearly as numerous as stars themselves. Some astronomical surveys indicate there could be as many as 100 billion brown dwarfs in the Milky Way alone. If even a small fraction of these objects host potentially habitable planets, they could represent one of the most numerous categories of life-supporting environments in our galaxy. Life evolving in these brown dwarf systems would experience a radically different environment than life on Earth, with profound implications for its adaptations and capabilities. The infrared illumination would require completely different photoreceptors than those used by Earth organisms, which have evolved to detect the visible wavelengths that predominate in sunlight. Vision, if it evolved at all, might operate in the infrared spectrum, perceiving heat differences rather than the colors we associate with sight. The potential for tidal locking would create extreme climate patterns, with intense heating on the day side and extreme cold on the night side. Successful organisms would need adaptations to cope with these sharp gradients, perhaps evolving migratory patterns that follow the terminator zone, where temperatures remain moderate. Alternatively, life might become highly specialized for either the perpetual day or eternal night, with distinct biospheres evolving in these contrasting environments. The close proximity to the brown dwarf would also expose planets to more intense solar flares and radiation events. Brown dwarfs, particularly younger ones, can produce energetic flares similar to those of red dwarf stars, though generally less powerful. Life would need to develop protection against these radiation bursts, perhaps through DNA repair mechanisms like those found in Earth's most radiation-resistant organisms, or by living beneath protective layers of water, soil, or ice. What about the possibility of intelligent life evolving in brown dwarf systems? While purely speculative, the unique conditions might drive evolution in directions quite different from Earth's evolutionary trajectory. The extreme environmental gradients caused by tidal locking could create strong selective pressures for advanced sensory capabilities and information processing, attributes that contribute to intelligence. The extraordinarily long stable periods provided by brown dwarfs would allow for extended evolutionary experimentation, potentially enabling the emergence of complex cognition through pathways unavailable in the shorter habitable timeframes of stellar systems. Any intelligent species evolving around a brown dwarf would develop a cosmic perspective vastly different from our own. Their sky would be dominated by their brown dwarf, appearing far larger than our Sun does from Earth due to their closer orbital distance, while emitting primarily heat rather than light. Stars would be visible only on the night side of their planet, and the concept of a day-night cycle might be entirely absent from their experience if their planet is tidally locked. Their astronomy would develop under different constraints as well. The brightness of their brown dwarf in infrared wavelengths would complicate observations of distant objects, while the potential for stronger magnetic fields and aurora-like phenomena might interfere with certain types of astronomical instruments. These challenges might drive the development of different observational technologies than those we've pursued on Earth. Beyond individual brown dwarfs, these objects sometimes form binary systems with true stars, creating environments with extraordinarily diverse illumination patterns. A planet in such a system might receive both visible light from the star and infrared radiation from the brown dwarf, potentially supporting hybrid ecosystems where different types of photosynthesis operate simultaneously. The combined gravitational influences would create complex orbital dynamics, potentially leading to extreme seasonal variations unlike anything experienced on Earth. Brown dwarfs also appear in binary pairs with other brown dwarfs or even with gas giant planets, blurring the distinction between different classes of objects. The boundary between the largest gas giants and the smallest brown dwarfs remains somewhat arbitrary, based primarily on mass rather than formation mechanism. And similar objects might support similar types of habitable environments regardless of their technical classification. This category-crossing nature of brown dwarfs highlights their unique position in astrobiology. Neither true stars nor planets, they offer hybrid environments that combine elements of both, potentially supporting forms of life that could not exist around either conventional stars or rogue planets. They represent a third option in our conception of habitable environments, not the sunlit surfaces of rocky planets in stellar habitable zones, nor the subsurface oceans of ice moons and rogue planets, but something altogether different, worlds bathed in infrared warmth, closely embraced by their failed stars. The study of potential life around brown dwarfs forces us to expand our astrobiological imagination, considering how biochemistry might adapt to energy sources, illumination patterns, and environmental conditions quite different from those that shaped life on Earth. It challenges us to think beyond the Earth analog paradigm that has dominated much of our search for extraterrestrial life, recognizing that habitable environments might exist across a far broader spectrum of astronomical context than traditionally considered. This expanded perspective becomes particularly important as we develop and deploy the next generation of astronomical instruments designed to search for biosignatures on exoplanets. If we focus exclusively on Earth-like planets orbiting Sun-like stars, we might overlook some of the most numerous potentially habitable environments in our galaxy. By considering the full range of possibilities, from conventional planets to brown dwarf systems to rogue worlds, drifting between stars, we maximize our chances of discovering extraterrestrial life in whatever form it might take. The role of brown dwarfs in potentially supporting life connects to broader questions about habitability throughout cosmic history. Brown dwarfs were likely more common in the early universe, when star formation occurred under different conditions than today. Their long-term stability means that habitable conditions around brown dwarfs could persist through cosmic epochs, where other environments become inhospitable due to stellar evolution or galactic events. Some astronomers have even suggested that as the universe ages and star formation declines, brown dwarfs and their planets might become the predominant habitable environments in the distant future. While stars like our Sun will eventually exhaust their fuel and die, brown dwarfs will continue their slow cooling process for trillions of years, potentially providing stable conditions for life long after conventional stars have faded away. In this sense, Brown dwarfs might represent not just an alternative habitat for life, but perhaps its ultimate refuge in the far future of our universe. If intelligent civilizations survive to witness the gradual dimming of stars, they might eventually migrate to brown dwarf systems as the last bastions of natural habitability in an aging cosmos. This long-term perspective reminds us that habitability is not a fixed property, but evolves over cosmic timescales. Environments that seem perfectly suited for life today, like Earth's surface, will eventually become uninhabitable as our sun brightens and ultimately dies. Conversely, environments that seem hostile now, like the close orbits around brown dwarfs, might offer sanctuary for life in both the present and the distant future. As we continue our search for life beyond Earth, brown dwarfs deserve special attention as potential hosts for habitable worlds. Their unique properties, cool temperatures, infrared radiation, strong magnetic fields, and extraordinary longevity create environments unlike anything in our solar system, potentially supporting forms of life adapted to conditions we can barely imagine. They represent one of the most intriguing possibilities in our expanding conception of where life might exist in the cosmos. And beyond brown dwarfs, in the more extreme environments where stars end their lives, lie even stranger possibilities. Black holes, the densest objects in the universe, where gravity becomes so intense that not even light can escape, might seem the antithesis of habitability. Yet even these cosmic extremes might harbor conditions where life could potentially emerge, tapping into energies and processes far removed from the gentle sunlight that powers Earth's biosphere. At the extreme end of cosmic phenomena lie black holes, regions where gravity becomes so intense that nothing, not even light, can escape. These gravitational giants, formed from the collapsed cores of massive stars or the mergers of dense objects, represent the most extreme environments in the known universe. The very mention of black holes evokes images of destruction, cosmic whirlpools tearing apart anything that ventures too close. Their immense gravitational fields stretching matter into thin strands before it disappears forever beyond the event horizon. Yet, in this seeming antithesis of habitability might lurk unexpected possibilities for life. Not within the black holes themselves. The laws of physics, as we understand them, preclude any organized structure surviving inside an event horizon, but in the complex, energy-rich environments that surround these cosmic leviathans. Could life exist in the vicinity of a black hole, harvesting energy from its gravitational influence, or the superheated matter swirling toward its dark maw? To explore this possibility, we must first understand what black holes actually are and how they influence their surroundings. Contrary to popular imagination, black holes aren't cosmic vacuum cleaners that suck in everything around them. Rather, they are extraordinarily dense concentrations of matter, where the normal repulsive forces between particles have collapsed, leaving gravity unopposed. At a certain distance, the event horizon, the escape velocity exceeds the speed of light, creating a boundary beyond which no information can return to the outside universe. The simplest black holes form when massive stars exhaust their nuclear fuel and collapse under their own gravity. These stellar mass black holes typically contain between 5 and several dozen times the mass of our Sun, compressed into a region smaller than a city. More massive black holes, containing millions or billions of solar masses, lurk at the centers of most galaxies, including our own Milky Way, which hosts a supermassive black hole called Sagittarius A star with a mass of about 4 million suns. The immediate vicinity of a black hole presents conditions utterly hostile to life as we know it. The intense gravitational gradient, the difference in gravitational pull between one point and another, would tear apart any macroscopic object, a process astronomers call spaghettification. Radiation levels near feeding black holes reach lethal intensities, and the extreme curvature of space-time creates environmental conditions unlike anything encountered on Earth. Yet, as we move outward from a black hole, these extreme conditions gradually moderate. At sufficient distance, the gravitational field becomes manageable, radiation levels decrease, and stable orbits become possible. In these outer regions, particularly around supermassive black holes, there exist zones where the laws of physics might permit organized systems, perhaps even life, to exist and potentially thrive. One of the most promising environments surrounds not isolated black holes, but those actively accreting matter. When gas, dust, or even stars fall toward a black hole, they form an accretion disk, a flattened, spiraling structure of superheated material. As this matter falls inward, gravitational energy converts to heat through friction, causing the disk to glow brilliantly across the electromagnetic spectrum, from radio waves to X-rays. These accretion disks represent some of the most energy-dense environments in the universe. A supermassive black hole actively feeding on surrounding matter can outshine the combined light of all the stars in its host galaxy, converting infalling mass to energy with an efficiency that dwarfs even nuclear fusion. This extraordinary energy output creates a radiative environment that would sterilize any Earth-like planet in the vicinity. However, not all black holes feed at the same rate or produce the same radiation environment. Many supermassive black holes go through cycles of activity, with periods of intense accretion followed by relative quiescence when the immediate supply of matter becomes depleted. During these quieter phases, the radiation environment around the black hole becomes less extreme, potentially allowing for conditions where complex chemistry or even life might exist. Furthermore, the energy output from accretion disks isn't uniformly distributed in all directions. Due to the physics of rotating black holes and their magnetic fields, much of the radiation channels into narrow jets, perpendicular to the accretion disk plane. These relativistic jets, composed of particles accelerated to near the speed of light, carry away enormous energy but leave other regions around the black hole relatively sheltered from the most intense radiation. In the shadow of the accretion disk, far from the paths of these jets, planets or other bodies might orbit with relative stability, receiving enough energy to maintain warm temperatures without being subjected to sterilizing radiation levels. These regions might create habitable zones around black holes, not defined by the Goldilocks distance for liquid water as with stars, but by the balance between energy input and potentially lethal radiation exposure. The concept gained scientific attention following theoretical work by physicist Jeremy Schnittman of NASA's Goddard Space Flight Center, who in 2019 published calculations suggesting that certain black hole configurations could indeed support habitable zones. According to his models, planets orbiting a small, non-rotating black hole could receive sufficient warming from the accretion disk's radiation to maintain surface temperatures suitable for liquid water, provided they orbit at an appropriate distance. Planets in such systems would experience a very different illumination pattern than Earth. Rather than a single-point light source like our Sun, these worlds would be bathed in light from the glowing arc of the accretion disk, creating complex patterns of day and night unlike anything in our solar system. The black hole itself would appear as a dark circle against this luminous background, a black sun that blocks the light from stars and gas behind it through gravitational lensing. The sky from such a world would be spectacular and alien. Stars behind the black hole would appear distorted or duplicated through gravitational lensing, forming perfect rings or multiple images around the dark silhouette. The accretion disk would dominate the sky, with its elongated arc of superheated gas, shifting through the spectrum from blue-white at its hottest inner regions to reddish at its cooler outer edges, far from the uniform blue of Earth's daytime sky. A planet orbiting a black hole might see a gradient of colors reflecting the complex radiation environment around it. Life in such an environment would need adaptations very different from those evolved under the yellow light of our sun. The radiation spectrum from an accretion disk contains higher proportions of X-rays and ultraviolet light, requiring robust protection against DNA damage. The magnetic fields around feeding black holes generate complex radiation belts that would pose additional challenges for surface-dwelling organisms. Yet these same energy sources might provide unique opportunities for life. The sharp energy gradients and magnetic fields could power exotic metabolic processes unavailable to Earth life. Organisms might evolve to harvest energy directly from the charged particles trapped in magnetic fields, or develop photosynthetic pigments tuned to the specific emission spectrum of accretion disk radiation. The gravitational environment around a black hole offers other unique possibilities. Einstein's general relativity tells us that gravity isn't simply a force, but a curvature of space-time itself. Near black holes, where this curvature becomes extreme, time dilation effects become significant. Time passes more slowly for observers closer to the black hole compared to those farther away. While often portrayed in science fiction as a means for interstellar travel or extended lifespans, these relativistic effects would have profound implications for any life evolving near a black hole. Biological processes closer to the black hole would proceed more slowly relative to those farther away, creating the possibility of evolutionary rate differentials based on orbital position. Species at different distances might evolve at different rates from each other, creating unique ecological relationships unlike anything on Earth. Beyond accretion disks, another potential habitat near black holes involves captured planets or rogue worlds. As galaxies evolve, stars and their planetary systems occasionally venture too close to the central supermassive black hole. The resulting tidal forces typically disrupt these systems, with some planets being ejected while others settle into stable orbits around the black hole itself. These captured planets would experience minimal direct heating from the black hole unless it maintained an active accretion disk. Instead, their thermal energy would come primarily from internal sources: radiogenic heat from the decay of radioactive elements in their cores, or tidal heating from orbital interactions with other captured planets or stars. Without intense stellar radiation, their surfaces might seem cold and barren, but their interiors could maintain sufficient warmth for subsurface biospheres similar to those proposed for rogue planets or icy moons. The most speculative, yet perhaps most intriguing possibility involves not natural planets, but artificial habitats constructed by advanced civilizations. If intelligent life were to emerge in a galaxy's central regions or migrate there over time, it might develop technologies to harness the extraordinary energy output of supermassive black holes. These civilizations might construct habitats specifically designed to capture energy from accretion disks or jets while shielding sensitive biological systems from harmful radiation. Such advanced engineering projects relate to concepts like Dyson spheres or swarms, which hypothetically would capture the majority of a star's energy output. Applied to black holes, similar constructs could potentially harvest energies far greater than available from even the most massive stars. A civilization capable of building such structures could create habitats supporting populations and energy usage, dwarfing anything possible with conventional stellar energy alone. The theoretical physics of rotating black holes suggests even more exotic energy harvesting possibilities. The Penrose process, proposed by mathematician Roger Penrose in 1969, describes a mechanism for extracting energy from a black hole's rotation by dropping objects into the ergosphere, a region outside the event horizon where space-time itself is dragged along with the black hole's spin. In theory, an advanced civilization might engineer systems to extract this rotational energy, providing power on scales difficult to imagine with current technology. Black holes also emit energy through a quantum mechanical process known as Hawking radiation, theorized by physicist Stephen Hawking in the 1970s. This radiation results from virtual particle pairs forming near the event horizon, with one particle falling in while the other escapes, effectively extracting energy from the black hole's mass. While Hawking radiation from stellar mass black holes would be incredibly faint, far too weak to support any biological processes, sufficiently advanced technologies might conceivably amplify or harness this output for specialized applications. Perhaps the most realistic near-term scenario for life around black holes involves not the immediate vicinity of these objects, but the dense star clusters that often surround them. particularly in the centers of galaxies. These regions contain stars packed hundreds of times more densely than in our solar neighborhood, creating opportunities for advanced life to spread between relatively closely spaced star systems. The cores of globular clusters, ancient spherical collections of hundreds of thousands of stars, represent similar environments even without central black holes. Stars in these regions orbit so closely that an advanced civilization could potentially travel between neighboring systems with far less difficulty than would be required from our isolated position in the galactic suburbs. Some astronomers have suggested these densely packed stellar regions as potential sites for interstellar civilizations to emerge and expand. The ethical implications of hypothesizing about intelligent life near black holes extend beyond mere scientific speculation. If habitable zones around black holes exist, they represent environments utterly different from Earth's, places where life would evolve under selective pressures and constraints foreign to our experience. Any intelligences emerging in such environments would likely perceive the universe differently than we do, with concepts of time, space, energy, and perhaps even causality shaped by their proximity to these extreme objects. Such differences highlight the danger of anthropocentrism in our search for extraterrestrial life. By focusing exclusively on Earth-like planets around Sun-like stars, we might overlook the possibility that life, including intelligent life, could adapt to conditions we instinctively consider hostile. The universe has had billions of years to experiment with chemistry and energy flows across an unimaginable variety of environments, from the temperate surface of Earth to the superheated accretion disks around black holes. Our understanding of life around black holes remains entirely theoretical, constrained by both our limited knowledge of extreme environment biology and the practical difficulties of studying black hole environments in detail. The closest known black hole to Earth, designated V616 Monocerotis, lies more than 3,000 light-years away, far beyond our current capacity for direct exploration. Even with our most powerful telescopes, detecting planets around black holes presents extraordinary technical challenges, particularly for smaller worlds that might fall within potential habitable zones. Future advances in astronomy may eventually allow us to identify planets orbiting black holes and study their properties, particularly those around supermassive black holes at galactic centers. The extreme gravitational lensing near black holes could potentially be leveraged for imaging distant objects with unprecedented resolution, perhaps even revealing atmospheric compositions or surface features of planets in these systems. The study of life's potential around black holes connects to broader questions about the fundamental limits of habitability throughout the universe. If life can adapt to the environment near the most extreme objects in existence, then perhaps biology is far more versatile and opportunistic than we've imagined. The boundaries between habitable and uninhabitable, between possible and impossible, might lie far beyond our current conceptions. This perspective challenges us to expand our astrobiological imagination, considering not just where life similar to Earth's might exist, but where any form of organized, self-sustaining complexity could emerge from the fundamental laws of physics and chemistry. Black holes, as the ultimate expression of these laws at their most extreme, provide a theoretical limit case for such considerations, a boundary condition for our understanding of life's possibilities. The energy gradients, complex radiation environments, and unique gravitational landscapes around black holes could potentially support novel forms of organization quite different from Earth life, but still recognizable as systems that process energy, maintain internal order, reproduce, and evolve. By stretching our conception of habitability to include these extreme environments, we prepare ourselves to recognize whatever forms of complexity the universe might have generated through its billions of years of cosmic evolution. Whether life actually exists around black holes remains an open question that may not be answered for generations. But by considering the possibility, by pushing our understanding of biology to its theoretical limits, we gain insights not just into potential exotic biospheres, but into the fundamental nature of life itself. We learn which aspects of Earth life represent universal constraints and which are merely contingent outcomes of our planet's specific conditions. As we continue to explore the universe through both observation and theory, the extreme environments around black holes remind us that nature's creativity likely extends far beyond what we've observed on our small, temperate world orbiting its ordinary yellow star. The cosmos may harbor forms of complexity and organization that would appear as alien to us as black holes themselves would appear to observers from a two-dimensional universe. The journey from considering stars essential for life to contemplating life around their antithesis, black holes, represents a profound evolution in our understanding of habitability. It suggests a universe not neatly divided into hospitable and inhospitable regions, but offering a continuous spectrum of possibilities, with life potentially emerging wherever energy flows through complex systems for sufficient time, regardless of how exotic those energy sources might be. But beyond natural habitability lies another frontier: the possibility that advanced civilizations might construct their own environments independent of planetary surfaces or natural energy sources. Might intelligent beings eventually build artificial worlds that transcend the limitations of planets altogether? Could technology enable life to exist in environments utterly unsuitable for its natural emergence? To explore this possibility, we must venture into the realm of megastructures, hypothetical engineering projects of staggering scale that could redefine what it means for an environment to be habitable. Throughout our exploration of life without stars, we focus primarily on natural environments, places where the fundamental forces of physics and chemistry might allow biology to emerge without the direct influence of stellar radiation. But what about artificial environments? Could advanced civilizations create their own habitable realms, independent of the warming rays of a star or the geothermal heat of a planet? Might technology eventually replace stars as the primary energy source for complex life? These questions lead us to consider some of the most ambitious engineering concepts ever proposed: megastructures that capture, redirect, or generate energy on scales comparable to stars themselves. The most famous of these theoretical constructs is the Dyson sphere, a hypothetical structure that completely encompasses a star to capture the majority of its energy output. Named after physicist Freeman Dyson, who formalized the concept in 1960, these megastructures represent the ultimate expression of a civilization's ability to harness energy. Contrary to popular depictions, a Dyson sphere wouldn't necessarily be a solid shell enclosing a star like a hollow planetary surface. Such a structure would face insurmountable engineering challenges, including gravitational stresses that would tear it apart. Instead, a more realistic version might consist of a vast swarm of individual satellites or habitats orbiting the star in a dense formation, a Dyson swarm that collectively intercepts most of the star's energy while avoiding the structural problems of a continuous shell. These satellites could serve various functions. Some might be dedicated power collectors, converting stellar radiation to usable energy. Others could function as habitats for biological or digital intelligences. Still others might house industrial facilities, computing infrastructure, or specialized research environments. The entire system would function as an integrated civilization-scale organism, processing energy and matter to maintain its complex internal organization. For a civilization facing the limitations of planetary resources, a Dyson swarm offers a logical expansion path. The total material available in planetary systems far exceeds what exists on habitable worlds alone. The asteroid belt in our solar system, for instance, contains enough material to construct millions of space habitats, each potentially offering living area comparable to a continent on Earth. The gas giants represent even larger reservoirs of raw materials. Jupiter alone contains more than twice the mass of all other planets combined. A civilization mining these resources could gradually construct a growing shell of habitats and energy collectors around its star, expanding its living space and energy budget far beyond what any single planet could provide. As the swarm grew denser, an increasing fraction of the star's energy would be captured and utilized rather than radiating uselessly into space. Eventually, the civilization might intercept most of the star's light, creating an artificial environment vastly larger than any natural planetary surface. But what does this have to do with life without stars? The relevance becomes clear when we consider the long-term implications of such development. A Dyson swarm doesn't eliminate dependence on stellar energy, but it fundamentally transforms the relationship between life and stars. Rather than being constrained to the narrow habitable zone where planetary surfaces maintain suitable temperatures, life would exist within engineered environments where conditions are precisely maintained regardless of distance from the star. More importantly, the energy harvested by such structures could potentially power artificial stars, fusion reactors, or other high-energy sources that could provide heat and light to habitats located far from any natural star. A civilization that masters fusion technology could create miniature suns to warm worldlets drifting in interstellar space, or to illuminate vast habitats in the outer reaches of star systems where natural sunlight grows faint. This technological progression suggests a potential evolutionary path for advanced civilizations, beginning on planetary surfaces warmed by natural stars, developing technology to harness increasing fractions of their star's energy, and eventually creating artificial energy sources that function effectively as star replacements. At this stage, the civilization would no longer be strictly dependent on its original star, though it might continue to harvest its energy while simultaneously developing independent power sources. The concept of artificial star replacement extends beyond mere energy provision. Advanced civilizations might eventually develop technology to control the life cycle of stars themselves, either by extending the lifespan of their existing stars or by creating new stellar objects from accumulated gas and dust. Such stellar engineering would represent a level of technological development far beyond anything within our current capabilities. Yet it remains theoretically possible given the fundamental physics of stellar processes. One proposed method for extending a star's lifespan involves stellar husbandry, removing hydrogen from a star's outer layers to reduce pressure at its core, thereby slowing the fusion reactions that will eventually lead to its expansion and death. For a star like our Sun, which will eventually expand into a red giant and incinerate the inner planets, such intervention could potentially extend the habitable period of its planetary system by billions of years. More ambitious proposals involve creating entirely new stars through controlled fusion ignition of gas giants or accumulated interstellar matter. While the energy requirements for such engineering would be enormous, a civilization that already controls a substantial fraction of its existing star's output might eventually accumulate sufficient resources for such projects. These artificial stars could be placed strategically to warm otherwise uninhabitable regions of space, effectively expanding the domain of potential life far beyond natural stellar systems. The ability to create and maintain artificial stars would fundamentally transform a civilization's relationship with its environment. No longer bound to the habitable zones around natural stars, it could expand throughout its home galaxy, establishing engineered habitats wherever resources exist. Life would become truly independent of natural stars, relying instead on technology to provide the energy and environmental conditions necessary for its continuation. This technological progression suggests a possible answer to the question of whether life can exist without stars. While natural biology might be limited to environments warmed by stars or alternative energy sources like geothermal heat, technologically advanced life could potentially free itself from these constraints, creating artificial environments suitable for biology wherever it chooses to expand. Such expansion need not be limited to biological life as we know it. Advanced civilizations might eventually develop digital consciousness or other forms of non-biological intelligence that could exist in environments utterly unsuitable for carbon-based life. These alternative forms of complexity might operate in the near vacuum of space, powered by direct stellar energy collection without requiring the moderate temperatures and atmospheric protection that biological organisms need. The concept of post-biological intelligence raises profound questions about the nature of life itself. If consciousness can exist in substrates other than cellular biology, then the domain of potential life expands far beyond environments suitable for carbon-based organisms. Digital or other non-biological intelligences might thrive in radiation environments that would sterilize conventional life, operate at temperature extremes where no cellular processes could function, or exist in distributed networks spanning interplanetary or even interstellar distances. Such entities would still require energy, the fundamental currency of all complex systems, but they might harvest it directly from radiation, electromagnetic fields, or other sources unsuitable for biological metabolism. Their relationship with stars would be fundamentally different from that of planetary biospheres, potentially allowing them to exist in regions where no natural biology could emerge or persist. The most advanced form of artificial environment might be what futurists call computronium, matter optimized for computation, potentially reorganizing entire planets or stellar systems to maximize information processing capacity. In such systems, intelligence wouldn't be localized to individual organisms or even discrete artificial entities, but would exist as patterns of information flow through the entire engineered system. The star would serve not as a source of habitat-warming radiation, but as a power supply for vast computational processes that might constitute life and consciousness in forms we can barely imagine. These speculative possibilities extend far beyond our current technological capabilities, but they remain consistent with our understanding of physics and the potential long-term development of intelligence. They suggest that while natural biology might remain largely dependent on stars or similar energy sources, the future of intelligent life might eventually transcend this limitation through technology, creating artificial environments where complexity and consciousness can thrive independent of natural stellar radiation. The concept of artificial habitats raises the question of detectability. How would we recognize such engineered environments if they existed elsewhere in our galaxy? Unlike natural planets with biosignatures like atmospheric oxygen or methane, artificial structures might be identified through their unusual infrared signatures, the waste heat they would inevitably emit, according to the laws of thermodynamics. A Dyson swarm, for instance, would absorb visible light from its central star and re-emit that energy as infrared radiation. From a distance, such a system would appear unusually dim in visible wavelengths, but abnormally bright in the infrared spectrum. Astronomers have actually conducted searches for such infrared excess objects, looking for potential signatures of advanced engineering around distant stars, under the broader field of research known as the search for technosignatures. While no conclusive evidence of megastructures has been found, several unusual objects have been identified that warrant further investigation. The star KIC 8462852, informally known as Tabby's star or Boyajian star, displayed unusual dimming patterns that some initially speculated might result from orbiting megastructures. Though natural explanations involving dust clouds now seem more likely, the excitement surrounding this discovery highlights our growing capability to search for signs of advanced engineering on stellar scales. The construction of artificial habitats and energy collection systems represents a potential evolutionary pathway for technological civilizations, a transition from planetary to stellar-scale engineering that might be common among sufficiently advanced species. If so, the galaxy might contain numerous examples of such development at various stages, from nascent Dyson swarms in their early construction phases to mature systems that have completely transformed their parent stars. This possibility connects to broader questions about the prevalence and longevity of technological civilizations in our galaxy. The famous Fermi Paradox asks why we haven't detected evidence of extraterrestrial civilizations if they are common. A question that becomes even more pointed when considering the potential visibility of stellar-scale engineering projects. The apparent absence of obvious megastructures in our astronomical observations suggests several possibilities. Perhaps technological civilizations are rare. Perhaps they typically don't survive long enough to develop such capabilities, or perhaps they develop along different engineering pathways than we anticipate. Alternatively, advanced civilizations might deliberately limit their visible impact on their stellar systems, either through technologies that minimize waste heat or through cultural choices that prioritize preservation over maximalist resource utilization. Just as human civilization is beginning to recognize the importance of environmental sustainability on Earth, more advanced societies might develop ethical frameworks that balance technological development with preservation of natural systems. The concept of artificial star replacement extends the possibilities even further. A civilization that develops the capability to create and maintain fusion reactors or other high-energy sources that effectively function as artificial stars would have truly transcended dependence on natural stellar radiation. Such technology could power habitats in the depths of interstellar space, far from any natural star, allowing life to expand throughout the galaxy regardless of the distribution of suitable planetary systems. These artificial stars need not resemble natural stellar objects in size or appearance. They might be relatively small fusion reactors providing energy to habitat clusters, or they might take more exotic forms. Miniature black holes maintained through controlled matter input, for instance, or matter-antimatter reactors converting mass directly to energy with perfect efficiency. The defining characteristic would be their ability to provide a continuous energy supply to maintain complex, organized systems, artificial biospheres, in regions where natural habitability would be impossible. The efficiency of such systems could potentially far exceed that of natural stars, while a planetary biosphere captures only a tiny fraction of its star's total energy output, about 1/1,000,000th in Earth's case. Engineered habitats could utilize energy with far greater efficiency, supporting much larger populations or more complex ecosystems than possible on natural planets. This efficiency connects to broader questions about the limits of life's complexity and the ultimate potential of intelligence. Natural ecosystems are constrained by the energy available from their stars, the efficiency of biological energy conversion, and the environmental conditions of their planets. Artificial environments, optimized for energy utilization and freed from planetary constraints, might support forms of complexity far beyond what has evolved naturally on Earth or could evolve on any natural world. The ultimate expression of this progression might be what futurists call a matryoshka brain, a nested series of computational shells around a star, each capturing the waste energy from the layer above and using it to power additional computation. Such a structure would utilize nearly all of the star's energy output for information processing, potentially supporting intelligence and complexity at scales inconceivable within planetary constraints. These speculative possibilities highlight a crucial distinction. While natural biology almost certainly requires some form of continuous energy input, whether from stars, geothermal sources, or chemical gradients, the specific form of that energy need not resemble our sun. Advanced technology might enable life to utilize energy sources far different from natural stellar radiation, effectively freeing biology from its traditional dependence on stars. This perspective suggests a potential answer to our original question: can life exist without stars? For natural biology emerging without technological intervention, the answer is qualified. Life likely requires either direct stellar energy or alternative natural sources like geothermal heat or tidal forces. But for technologically advanced life, the answer expands. Through artificial habitats, engineered energy sources, and potentially post-biological forms of intelligence, life might eventually transcend its dependence on natural stars altogether. This evolutionary trajectory, from planetary biology to stellar-scale technology to potential independence from natural stars, might represent a common developmental pathway for intelligent life throughout the universe. If so, the most advanced civilizations in our galaxy might already exist, primarily in engineered environments, having transcended the planetary surfaces where their ancestral biology first evolved. The search for such civilizations connects to our broader quest to understand life's place in the cosmos. By considering not just where life like our own might exist, but where any form of complexity and intelligence might emerge and develop, we expand our perspective beyond Earth analog environments to the full spectrum of possibilities permitted by physics and chemistry. This broader view suggests a universe not sharply divided between habitable and uninhabitable regions, but offering a continuous gradient of possibilities, from the most favorable natural environments where biology might emerge spontaneously, to marginal zones where life could survive but not originate, to regions where only technology could create and maintain the conditions necessary for complexity. Our exploration of artificial habitats returns us to a profound question. What is the true essence of life? Is it necessarily carbon-based cellular biology, or might it encompass any self-sustaining system that processes energy, maintains internal organization, reproduces, and evolves? If we accept the latter, more inclusive definition, then the potential domain of life extends far beyond the narrow zones traditionally considered habitable, encompassing engineered environments that might exist anywhere. Resources can be gathered and energy harvested. This perspective transforms our understanding of habitability from a property of natural environments to a potential state that intelligent life itself might create wherever it expands. Rather than being passive inhabitants of habitable worlds, advanced civilizations become active creators of habitability, engineering environments suitable for their continued existence and development regardless of natural conditions. The ultimate expression of this capability might be what could be called portable habitability, self-sufficient habitats carrying life between the stars, each an artificial microworld maintaining the conditions necessary for biology or post-biological intelligence. These worldships, powered by fusion reactors or other artificial energy sources, would truly represent life independent of stars, not because they don't require energy, but because they carry their energy sources with them, creating miniature biospheres in the vast darkness between stellar systems. As we consider the possibilities of artificial habitats and star replacements, we're reminded that our exploration of life's potential throughout the universe must include not just what nature might create through undirected processes, but what intelligence might engineer through directed application of physical principles. The future of life in the cosmos may depend not just on finding habitable environments, but on creating them, extending the domain of complexity and consciousness far beyond the limits imposed by natural habitability. But while artificial habitats represent a potential future for advanced civilizations, most life in the universe likely still exists in natural environments, constrained by the energy sources and conditions available without technological intervention. Beyond the dramatic possibilities of megastructures and artificial stars, we should also consider more modest natural environments that might support life, far from the warming influence of stars. The outer reaches of our own solar system, for instance, contain fascinating worlds that might harbor environments suitable for simple biology despite their great distance from the Sun. Far beyond the warmth of our Sun, in the dim outer reaches of our solar system, lie vast regions populated by countless icy bodies, frozen time capsules from the formation of our planetary system. These regions, the Kuiper Belt and the more distant Oort Cloud, have long been considered little more than cosmic deep freezers, places where volatile compounds ejected from the inner solar system collect in a perpetual frigid stasis. But could these seemingly inhospitable frontier zones harbor environments where life might exist, despite their enormous distance from the Sun's warming rays? The Kuiper Belt begins beyond the orbit of Neptune, approximately 30 astronomical units from the Sun, 1 astronomical unit being the average distance between Earth and the Sun, and extends to about 50 astronomical units. This donut-shaped region contains millions of icy bodies, most smaller than 100 kilometers in diameter, composed primarily of frozen methane, ammonia, water, and other volatile compounds that could only condense at the extremely low temperatures of the outer solar system. Beyond the Kuiper Belt, extending from about 1,000 to 100,000 astronomical units from the Sun, lies the Oort Cloud, a vast spherical shell of icy objects marking the outer boundary of our solar system. Unlike the relatively flat Kuiper Belt, The Oort Cloud surrounds the Sun in all directions, containing trillions of icy bodies that orbit our star at distances so great that light takes days, weeks, or even more than a year to reach them from the Sun. At such extreme distances, solar heating becomes negligible. The surface temperature of an object in the Kuiper Belt might hover around -200 degrees Celsius, while those in the Oort Cloud approach the background temperature of space itself, a frigid -270 degrees Celsius. These temperatures lie far below the freezing point of water, and even below that of gases like nitrogen and oxygen, creating surface environments where most familiar chemical processes would grind to a near halt. Yet despite these seemingly prohibitive conditions, recent discoveries have forced scientists to reconsider the potential for habitability in these distant regions. The key insight comes from closer to home, with the exploration of dwarf planets like Pluto and other large Kuiper Belt objects. When NASA's New Horizons spacecraft flew past Pluto in 2015, it revealed a surprisingly dynamic world with diverse terrains, evidence of recent geological activity, and signs that liquid water might exist beneath its frozen surface. Pluto's interior appears to contain sufficient radioactive elements that, as they decay, generate enough heat to potentially maintain a subsurface ocean of liquid water mixed with ammonia, which acts as an antifreeze. Similar conditions might exist on other large bodies in the Kuiper Belt, such as Eris, Makemake, and Haumea, as well as on Neptune's moon Triton, which is believed to be a captured Kuiper Belt object. The discovery of potential subsurface oceans on these distant worlds parallels what we've already observed on the icy moons of Jupiter and Saturn. If bodies as far from the Sun as Pluto can maintain liquid water beneath their surfaces, then habitability in our solar system extends much farther than traditionally assumed. The warming rays of the Sun become irrelevant for these potential habitats, which derive their heat entirely from internal sources, primarily radioactive decay in their rocky cores. What about even more distant objects in the Oort Cloud? Individual Oort Cloud bodies remain beyond our current observational capabilities, but we can study the comets that occasionally plunge into the inner solar system from this distant reservoir. Analysis of these comets reveals they contain complex organic compounds, water ice, and various minerals, all essential ingredients for life as we know it. While smaller Oort Cloud objects likely lack sufficient mass to generate significant internal heat, larger bodies might still harbor warm interiors despite their frigid surfaces. The potential for habitability in these distant regions connects to broader questions about the prevalence of life throughout the galaxy. If liquid water environments can exist so far from a star, maintained solely by internal heat sources, then similar conditions might occur on countless bodies throughout the Milky Way, not just on planets orbiting within traditional habitable zones, but on large moons, dwarf planets, and other objects far from stellar warmth. This realization dramatically expands the potential inventory of habitable environments in our galaxy. The number of rogue planets, worlds ejected from their home systems to wander interstellar space, likely exceeds the number of stars. If these bodies can maintain internal heat and subsurface oceans through radioactive decay, they could represent a vast category of potential habitats previously overlooked in our assessment of where life might exist. Life in these distant, light-starved environments would differ fundamentally from the photosynthesis-based ecosystems that dominate Earth's surface. Without sufficient sunlight to power photosynthesis, any organisms in subsurface oceans beneath Kuiper Belt or Oort Cloud objects would rely on chemosynthesis, extracting energy from chemical reactions between water and minerals in the rocky core. Similar ecosystems exist on Earth around deep-sea hydrothermal vents, where microorganisms harness energy from the oxidation of hydrogen sulfide, methane, and other compounds released from the planet's interior. These communities support complex food webs, including specialized bacteria, archaea, and even multicellular organisms like tube worms, shellfish, and crustaceans, all existing without any input from photosynthesis. The subsurface oceans of Kuiper Belt objects might host similar ecosystems, with microorganisms extracting energy from reactions between water and minerals in the rocky core. Over time, such environments might develop complex chemosynthetic food webs, analogous to Earth's vent communities. While the total energy available would be less than in photosynthetic ecosystems, it could potentially support specialized organisms adapted to these low-energy, stable environments. One advantage these distant worlds might offer for potential life is extraordinary stability. Without seasonal changes, climatic fluctuations, or the threats of meteorite impacts which would be slowed by thick ice shells, subsurface oceans in the outer solar system could provide constant conditions over billions of years. This stability might allow for the gradual evolution of highly specialized organisms exquisitely adapted to their specific environment. The isolated nature of these habitats would also create fascinating evolutionary dynamics. Each subsurface ocean would form a separate ecosystem, isolated from others by vast distances and impenetrable ice barriers. Life emerging independently in these separate oceans would likely follow distinct evolutionary pathways, potentially developing fundamentally different biochemistries and adaptive strategies. Even if life didn't originate independently in these environments, it might have been seeded through panspermia, the transfer of microorganisms between worlds via meteorite impacts or other mechanisms. Simple organisms from Earth or Mars might have been ejected into space by large impacts early in solar system history, eventually finding their way to the outer regions where they colonized subsurface oceans of distant worlds. This possibility raises an intriguing notion. The outer solar system might harbor descendants of Earth life, evolved over billions of years in isolation to become something unrecognizably alien despite sharing a common origin with terrestrial organisms. These distant cousins would have adapted to entirely different selective pressures, low energy availability, constant darkness, dissolved gases and minerals unlike those in Earth's oceans, potentially developing novel metabolic strategies and sensory systems unlike anything found on our home planet. The most tantalizing targets for potential habitability in the Kuiper Belt include not just Pluto, but other large dwarf planets like Eris, slightly more massive than Pluto, and Makemake. Less is known about these more distant objects, but their size suggests they likely generated sufficient heat during formation to melt their interiors, and they may contain enough radioactive elements to maintain subsurface liquid water despite the extreme cold of their surfaces. Haumea presents a particularly interesting case. This elongated dwarf planet rotates extremely rapidly, completing a full rotation in just under 4 hours, and appears surrounded by a ring system. Its unusual shape and rotation suggest a violent collision in its past, which would have generated tremendous heat that might have persisted long enough to initiate chemical reactions favorable to prebiotic chemistry or even simple life forms. Quasar, another large Kuiper Belt object, shows evidence of cryovolcanism, eruptions of liquid or vapor from its interior through its icy crust. This activity indicates a warm subsurface layer, possibly a liquid water ocean mixed with ammonia or other antifreeze compounds. Similar features have been observed on several other distant bodies, suggesting that liquid environments beneath icy crusts might be common throughout the outer solar system. Beyond these known bodies lie countless others waiting to be discovered. Current observational techniques can only detect the largest Kuiper Belt objects, leaving millions of smaller bodies unsurveyed. The Oort Cloud remains even more mysterious, with only its innermost regions accessible to current observational technology. Future telescopes might reveal large, planet-sized objects in these distant regions, some potentially harboring their own subsurface oceans. The vastness of these outer regions becomes apparent when we consider their population estimates. Astronomers believe the Kuiper Belt contains hundreds of thousands of objects larger than 100 kilometers in diameter and millions of smaller bodies. The Oort Cloud, far larger in volume, might contain trillions of icy objects, some potentially as large as Earth or larger. If even a small fraction of these bodies maintain subsurface liquid environments, the outer solar system could host more potentially habitable environments than the inner solar system's traditionally habitable zone. Water isn't the only potential solvent for life in these distant regions. At the extremely low temperatures of Kuiper Belt and Oort Cloud surfaces, chemicals that are gases on Earth become liquids or solids. Methane and ethane, for instance, remain liquid at temperatures around -180 degrees Celsius, far below water's freezing point, but potentially warm enough to support exotic biochemistries. Saturn's moon Titan demonstrates the potential for methane/ethane biochemistry with its lakes and seas of liquid hydrocarbons. Similar environments might exist on the surfaces of distant Kuiper Belt objects, creating the possibility of life forms using entirely different chemical foundations than Earth organisms. Such life would metabolize extremely slowly by Earth standards due to the low temperatures. But over the billions of years these environments have existed, complex chemical systems might have emerged. Ammonia-water mixtures represent another potential medium for exotic life. When mixed with water, ammonia acts as an antifreeze, allowing liquids to exist at temperatures as low as -100 degrees Celsius. Some models of Kuiper Belt object interiors suggest ammonia-water oceans might be common, providing environments where chemical reactions could proceed despite the extreme cold of the surrounding space. These considerations remind us that habitability must be assessed not through Earth-centric assumptions about temperature and chemistry, but through fundamental principles of what allows for complex, self-organizing systems, where energy flows through chemical systems with sufficient stability and appropriate solvents for molecular interactions. The potential for life cannot be dismissed merely because conditions differ dramatically from Earth's surface. The exploration of these distant worlds has only just begun. NASA's New Horizons mission provided our first close look at a Kuiper Belt object when it flew past Pluto in 2015, revealing a surprisingly active world with diverse surface features and potential subsurface oceans. The spacecraft subsequently investigated a smaller Kuiper Belt object called Arakoth, previously known as Ultima Thule, providing insights into the primordial building blocks of planets. Future missions might include orbiters or even landers designed to study the larger Kuiper Belt dwarf planets in detail, potentially using radar or other technologies to probe beneath their icy crusts and detect subsurface oceans directly. The technical challenges are formidable. The extreme distances require nuclear power sources rather than solar panels, and communication delays stretch to hours, but the scientific rewards would be immense. The Oort Cloud presents even greater challenges for direct exploration. At distances of thousands to tens of thousands of astronomical units, spacecraft using current propulsion technology would require centuries to reach even the innermost regions of this vast shell. Advanced propulsion systems, perhaps utilizing nuclear pulses or solar sails, might someday enable missions to these extreme distances. But for now, we must rely on theoretical models and observations of comets that originate there. In considering the habitability of these distant regions, we confront a fundamental question: how common is life in the universe? If biology can exist not just on the surfaces of planets warmed by stars, but in subsurface oceans maintained by internal heat, then the potential environments for life expand dramatically. Every large icy body in every planetary system might harbor its own isolated biosphere, hidden beneath frozen crusts far from the light of stars. This perspective transforms our understanding of habitability from a rare condition requiring precise stellar and planetary parameters to a common state, existing wherever sufficient mass allows for internal heating. Life, in this view, might be not the exception, but the rule, emerging wherever liquid environments persist for sufficient time with the necessary chemical ingredients. The possibility of life in the Kuiper Belt and beyond connects to our search for habitability throughout the galaxy. If subsurface oceans exist within dwarf planets in our outer solar system, similar environments likely occur throughout other planetary systems as well. The conditions that allow for liquid water beneath the frozen surface of Pluto would apply equally to similar-sized objects orbiting other stars, or drifting through interstellar space as rogue planets. This expanded conception of habitability suggests that life might be far more widespread than traditionally assumed, rather than being confined to the narrow habitable zones around stars where surface water can exist. Biology might flourish in subsurface environments throughout the galaxy, independent of stellar heating. The implications for astrobiology and our search for extraterrestrial life are profound. We may need to look not just to Earth-like planets around Sun-like stars, but to the icy worlds of the outer solar system and beyond. The frozen worlds of the Kuiper Belt and Oort Cloud thus offer more than a glimpse into the solar system's past. They provide potential windows into life's adaptability and distribution throughout the cosmos. In their frigid isolation, far from the sun's warming influence, they challenge our assumptions about where life can exist and what forms it might take, reminding us that biology's boundaries likely extend far beyond the comfortable conditions of our home planet. Yet even these distant realms represent just one category of non-traditional habitat. Beyond the Kuiper Belt and Oort Cloud lie even stranger possibilities, environments where the fundamental forces and materials of the universe combine in ways with no analogue on Earth. These exotic conditions might support forms of organization radically different from terrestrial biology, yet potentially recognizable as lifelike in their complexity and self-sustaining nature. To explore these furthest frontiers of potential habitability, we must venture into the realm of theoretical physics and speculative biology, examining how exotic matter and energy sources might create novel opportunities for complexity to emerge. Beyond the conventional boundaries of planets, moons, and even the distant icy bodies of the Kuiper Belt and Oort Cloud lie realms where physics operates in ways wholly unfamiliar to our everyday experience. These exotic domains, where dark matter accumulates, where quantum effects dominate, or where extreme gravitational fields warp space-time itself, seem utterly inhospitable to life as we know it. Yet could these very environments, so alien to our Earth-evolved biology, harbour their own unique forms of organization and complexity? Might life exist, not just without stars, but based on principles and energy sources that have no analogue in familiar biological systems? To explore this frontier of possibility, we must first confront one of the greatest mysteries in modern physics: dark matter. Making up approximately 85% of all matter in the universe, dark matter remains invisible to conventional detection methods, revealing itself only through its gravitational effects on visible matter and radiation. While we can map its distribution through gravitational lensing and galactic rotation patterns, its fundamental nature remains elusive despite decades of increasingly sophisticated experiments. Leading theories propose that dark matter consists of as-yet undiscovered subatomic particles that interact only weakly with ordinary matter. These hypothetical particles, perhaps WIMPs, weakly interacting massive particles, or axions, would pass through normal matter almost as if it weren't there, making them extraordinarily difficult to detect directly. Yet collectively, their gravitational influence shapes the largest structures in the universe, from galaxy clusters to the cosmic web of matter stretching across billions of light years. Could this mysterious substance, which permeates our own Milky Way galaxy and extends far beyond its visible disk, support structures akin to life? The question strikes many physicists as outlandish, given that dark matter particles interact so weakly with each other and with ordinary matter. Unlike normal atoms, which can form complex molecules through electromagnetic forces, dark matter particles would seemingly lack the necessary interactions to create organized structures with the complexity life requires. Yet some theorists have proposed speculative models where dark matter might exhibit more complex behaviors than currently assumed. Certain versions of dark matter theory include dark electromagnetism, or similar forces that would act between dark matter particles, much as electromagnetic forces act between normal atoms. Such interactions could hypothetically allow for dark chemistry, complex binding relationships between dark matter particles that might, under the right conditions, lead to self-organizing systems. Theoretical physicist Lisa Randall of Harvard University has explored a variation of this concept, proposing a model where a portion of dark matter might form a thin disk within the Milky Way, similar to, but distinct from the visible disk of stars and gas. This dark disk would interact gravitationally with visible matter, but would have its own internal dynamics, potentially including regions where dark matter particles interact more strongly with each other than with normal matter. In such regions, could complex patterns emerge from these interactions, patterns that process energy, maintain internal organization, and perhaps even reproduce? The answer remains deeply speculative, but the possibility cannot be dismissed outright. If dark matter particles can interact through forces beyond mere gravity, and if those interactions can create stable structures of increasing complexity, then something analogous to life might conceivably exist in the dark sector of the universe's fundamental constituents. Such dark life, if it exists, would bear little resemblance to Earth biology. Without the electromagnetic interactions that enable chemistry as we know it, dark matter organisms would operate according to entirely different principles. They might exist on vastly different scales of size and time, perhaps as diffuse structures spanning light years, or alternatively as microscopic patterns within dark matter halos. Their metabolism would involve not the chemical energy transformations familiar to Earth life, but exotic processes involving whatever forces govern dark matter interactions. The concept forces us to confront fundamental questions about life's definition. If we define life functionally as systems that maintain internal organization against entropy, process energy, reproduce, and evolve through natural selection, then the specific chemistry becomes less important than these abstract organizational principles. Dark matter systems that fulfilled these criteria would qualify as life in this broader sense, even if their physical basis differed radically from carbon-based biology. The challenges to detecting such exotic life forms would be formidable. Since dark matter interacts so weakly with ordinary matter, our conventional instruments would register little direct evidence of dark matter organisms, even if they permeated the very space we occupy. We might notice them only through subtle gravitational effects or rare weak force interactions that conventional physics cannot readily explain. Some researchers have suggested that dark matter life might reveal itself through unexplained patterns in cosmic ray distributions, anomalous energy emissions from seemingly empty regions of space, or statistical irregularities in the large-scale structure of dark matter halos. These signatures would be extraordinarily difficult to distinguish from conventional astrophysical phenomena, requiring both advanced detection technology and theoretical frameworks to interpret possible biological signatures. Moving beyond dark matter, other exotic energy sources might potentially support novel forms of organization. Vacuum energy, the residual energy of empty space predicted by quantum field theory, represents one such possibility. Current physics suggests that even perfect vacuum contains energy through quantum fluctuations, where particle-antiparticle pairs briefly pop into existence before annihilating. Could complex systems emerge within these quantum fluctuations, perhaps existing in superposed states rather than the definite configurations of conventional matter? Such quantum-based life would operate according to principles utterly foreign to our macroscopic experience. Rather than distinct organisms with clear boundaries, these entities might exist as probability distributions, their bodies defined by wave functions rather than material structures. Their interactions would involve quantum processes like entanglement and superposition rather than chemical reactions, and their relationship with time might differ fundamentally from the linear progression experienced by biological organisms. Another exotic possibility involves topological defects in spacetime, regions where the fabric of space itself contains anomalies resulting from phase transitions in the early universe. These defects, which include cosmic strings, domain walls, and monopolies, represent boundaries between regions with different vacuum states. The energy concentrated in these defects could hypothetically support complex systems, particularly in the intersection regions where multiple defects meet. neutron stars present yet another environment where exotic forms of organization might emerge. These stellar remnants, formed from the collapsed cores of massive stars, contain matter compressed to densities greater than an atomic nucleus. Under such extreme conditions, conventional atoms cannot exist. Instead, matter organizes into states unlike anything found elsewhere in the universe, perhaps including crystalline structures of pure neutrons or strange quark matter. Could complex, lifelike systems emerge within the crusts or interiors of neutron stars? Some theoretical physicists, including Frank Drake, have speculated about nuclear molecules forming in neutron star crusts, where patterns of nuclear, rather than electronic bonds, create structures that might process energy, replicate, and even evolve. The timescales for such processes would be extraordinarily compressed. Events that would take years in conventional biology might transpire in microseconds in the extreme environment of a neutron star surface. On neutron star surfaces, magnetic fields billions of times stronger than Earth's create additional exotic conditions. These magnetic fields constrain the movement of charged particles, potentially creating stable patterns that persist despite the star's extreme temperature. Theoretical models suggest that complex structures similar to crystals or molecules might form within these magnetically ordered regions, processing energy from the neutron star's radiation and magnetic flux. Expanding our view further, some physicists have proposed that black holes themselves might support complex information processing analogous to life or consciousness. The event horizon of a black hole represents a unique boundary in space-time where information appears to be both destroyed and preserved according to different physical principles. This paradox has led to speculations about black holes as information processing systems of extraordinary complexity. Physicist Lee Smolin has even suggested that black holes might reproduce in a sense, with each one spawning a new universe on the other side of its singularity. If properties of the parent black hole influence the fundamental constants of these daughter universes, and if universes with more black holes produce more offspring, a process analogous to natural selection might drive the evolution of universe-generating black holes. While not life in any conventional sense, such a process would represent a form of complexity and reproduction at the largest possible scale. Moving from the largest scales to the smallest, hypothetical subatomic structures like magnetic monopoles or cuballs, stable configurations of fields predicted by some extensions of particle physics, might support complex patterns that process energy and maintain organization. While individual particles are too simple to qualify as lifelike, collective systems of these exotic particles interacting through fundamental forces could potentially develop emergent properties similar to those we associate with biological systems. All these speculative possibilities share a common theme. They expand our conception of life beyond its carbon-based, water-solvent, temperature-restricted Earth incarnation to include any system that maintains complexity through energy processing, regardless of its material basis. This perspective sees life not as a specific chemical system, but as a class of organizational patterns that can emerge wherever the laws of physics permit sufficient complexity and stability. This broader definition connects to information theory and thermodynamics, viewing life as systems that maintain low entropy, high organization, locally, while increasing entropy globally through energy degradation. The specific mechanisms and materials involved become secondary to these abstract organizational principles, allowing for the possibility of life based on wildly different physical foundations than Earth biology. Returning to dark matter, some cosmologists have proposed that dark matter might form structures analogous to stars, planets, and even galaxies, parallel systems invisible to our conventional observations, but interacting through gravity with the visible universe. If dark matter can form such structures, and if some subset of dark matter particles interact through forces beyond gravity, then the possibility of dark matter life cannot be dismissed outright, however speculative it remains. The search for such exotic life forms presents extraordinary challenges. Unlike conventional biology, which leaves clear biosignatures in planetary atmospheres or surface features, exotic life might leave few traces detectable with current technology. We would need to develop new observational techniques specifically designed to detect anomalous patterns in dark matter distribution, unusual energy emissions, or statistical deviations from purely physical processes. Some researchers have suggested focusing on regions where dark matter concentrates densely, such as the centers of galaxies or dwarf satellite galaxies, with high dark matter to visible matter ratios. If dark matter exhibits complex self-organization, these regions might show subtle but detectable deviations from the behavior predicted by purely gravitational models. Similar approaches might apply to other exotic environments, looking for patterns that suggest non-random, self-organizing processes at work. The field of astrobiology, traditionally focused on carbon-based life in conventional habitable zones, has begun to expand its conceptual frameworks to include these more speculative possibilities. Organizations like the NASA Astrobiology Institute now sometimes include research on alternative biochemistries and exotic life forms, recognizing that our search for extraterrestrial life should encompass the full spectrum of possibilities permitted by physics and chemistry. This broader perspective forces us to confront the anthropocentrism inherent in many of our assumptions about life. Having evolved on a temperate, water-rich planet, orbiting a stable main sequence star, Earth life reflects the specific conditions of this environment. Our biology depends on liquid water, carbon-based molecules, and the electromagnetic force for chemical bonds. But these represent just one possible configuration among many allowed by the fundamental laws of physics. Life elsewhere might operate according to entirely different principles, utilizing energy sources and organizational mechanisms unlike anything in Earth biology. Dark matter organisms, if they exist, might perceive the universe through interactions we barely understand, operating on timescales and size scales that make them effectively invisible to our observations. What we consider exotic and improbable reflects our limited perspective as carbon-based organisms adapted to a specific planetary environment. This recognition challenges us to develop more inclusive frameworks for recognizing life or lifelike systems across the universal spectrum of possibilities. Rather than looking exclusively for Earth analog biosignatures like oxygen atmospheres or organic compounds, astrobiologists increasingly focus on broader indicators of complexity and non-equilibrium processes, signatures that might reveal organization regardless of its specific chemical or physical basis. The burgeoning field of complex systems theory offers tools for this broader search, examining how order emerges from chaos across diverse systems, from cellular automata to neural networks, financial markets to weather patterns. These abstract models identify universal principles of self-organization that might apply not just to carbon-based biology, but to any system with sufficient complexity and energy flow, regardless of its material foundation. From this perspective, life represents not a specific chemical phenomenon, but a broader class of self-organizing, energy-processing systems that can emerge wherever physics permits sufficient complexity. Earth life represents one expression of this universal tendency toward organization, but others might exist based on dark matter, neutron star matter, quantum fluctuations, or physical systems we've yet to discover or imagine. This expanded view transforms our understanding of habitability from a narrow focus on planet-star relationships to a universe-spanning survey of where complexity might emerge. Life becomes not a rare accident requiring precise conditions, but a natural consequence of fundamental physical principles, potentially manifesting wherever energy flows through systems capable of increasing their internal organization. The implications extend beyond scientific curiosity to profound philosophical questions about humanity's place in the cosmos. If life or lifelike complexity can emerge across such a diverse spectrum of environments, from planetary surfaces to dark matter halos to neutron star crusts, then the universe might harbor forms of organization far more diverse and numerous than our traditional conception of habitability suggests. This possibility doesn't diminish the uniqueness of Earth life or human consciousness, but places them within a broader context of universal complexity. Rather than representing the only example of organized complexity in an otherwise chaotic cosmos, Earth life might constitute one expression of a more general tendency toward organization inherent in the laws of physics themselves. Such perspective shifts connect to ancient philosophical questions about whether the universe intrinsically tends toward increasing complexity and order. From Aristotle's teleology to modern concepts of self-organization, thinkers have long debated whether complexity represents a fundamental property of reality or merely a statistical outlier in an otherwise entropic universe. The possibility of exotic life forms based on principles and materials vastly different from Earth biology suggests that complex organization might indeed be a natural, even inevitable outcome of physical laws operating across diverse conditions. This doesn't necessarily imply purpose or design in a traditional sense, but rather that the fundamental equations governing reality contain inherent tendencies towards pattern formation, complexity, and self-organization. Life, in its broadest sense, might represent not a miraculous exception to cosmic disorder, but an expression of underlying mathematical principles that manifest wherever conditions permit. As we contemplate these exotic possibilities, we should remember that our understanding remains profoundly limited by both our observational capabilities and our conceptual frameworks. Dark matter itself was unknown to science until the 20th century, and its fundamental nature remains one of physics' greatest unsolved mysteries. Other exotic environments like neutron star crusts, black hole horizons, or quantum vacuum states lie even further beyond our direct observation, accessible only through indirect measurements and theoretical models. Our capability to recognize life or lifelike systems in such environments is similarly constrained. Having evolved to perceive and interact with other carbon-based organisms on a planetary surface, our intuitions about what constitutes life may blind us to forms of organization operating according to entirely different principles. The history of science shows repeatedly how anthropocentric assumptions have limited our understanding of natural phenomena, from geocentric cosmology to human exceptionalism in cognition. Overcoming these limitations requires both technological advancement and conceptual flexibility. Future observatories with unprecedented sensitivity might detect subtle patterns in dark matter distribution or exotic energy emissions that current instruments miss. Similarly, expanding our theoretical frameworks to encompass more diverse definitions of life and complexity might allow us to recognize biosignatures previously overlooked because they didn't match our Earth-centric expectations. This expansive view of life's possibilities connects to one of humanity's most profound questions: are we alone in the universe? If life can exist not just on Earth-like planets, but in environments as exotic as dark matter halos, neutron star crusts, or the quantum vacuum, then the universe might harbor complex organization far more abundantly than our traditional conception of habitability suggests. We might exist not in a largely sterile cosmos with occasional oases of life, but in a universe teeming with diverse forms of complexity, most operating according to principles we've barely begun to understand. Such recognition would fundamentally transform our cosmic perspective. Rather than representing a singular miracle in an otherwise lifeless universe, Earth and its biosphere would constitute one expression of a more general tendency toward organization inherent in reality itself. Human consciousness, remarkable as it is, would exist within a broader spectrum of complexity spanning environments and physical systems throughout the cosmos. As we continue exploring the boundaries of where life might exist without stars, these exotic possibilities remind us that our imagination often falls short of the universe's creative potential. The laws of physics, operating across scales from subatomic particles to galactic superclusters, from the vacuum of space to the densest neutron stars, may generate forms of organization as far beyond our current conception as a human mind is beyond a single cell. In contemplating such possibilities, we practice a form of cosmic humility, recognizing the limitations of our Earth-evolved perspective while stretching toward a more inclusive understanding of life's potential throughout the universe. Whether dark matter harbors its own exotic ecologies, or neutron stars host ultra-rapid life forms operating in microseconds rather than years, or other forms of organization exist that we lack even the vocabulary to describe, the universe's capacity for complexity likely exceeds our wildest speculations. This expansive vision of life's potential domain brings us full circle to our original question: could life exist without stars? Beyond the more conservative possibilities of subsurface oceans warmed by radioactive decay or tidal heating, beyond even the speculative realm of life adapted to brown dwarfs or black hole accretion disks, lies this furthest frontier: environments where the very definition of life expands to include systems operating according to exotic physics in realms utterly unlike Earth's comfortable surface. The answer, at this furthest boundary of speculation, becomes not just yes, life could exist without stars, but life might exist in forms and environments so diverse that stars represent just one type of habitat among countless others throughout the cosmic spectrum. This perspective transforms our understanding of habitability from a rare, specific set of conditions to a universal principle manifesting across diverse systems wherever energy flows through complex patterns. As we redefine our notion of life to focus on abstract organizational principles rather than specific chemical implementations, we open our minds to the full creative potential of a universe governed by physical laws that inherently tend toward complexity. In this expansive view, life without stars becomes not merely possible, but perhaps inevitable, an expression of the same fundamental principles that have generated complexity across scales from atoms to ecosystems, from planets to galactic superclusters. Throughout our journey exploring the possibility of life without stars, we've repeatedly confronted a fundamental question: what exactly is life? Our traditional definitions, shaped by Earth's biosphere, often focus on specific chemical and physical attributes: carbon-based molecules, liquid water as a solvent, metabolism driven by redox chemistry, and information stored in nucleic acids. But as we've ventured into environments radically different from Earth's surface, from the subsurface oceans of distant icy moons to the theoretical realm of dark matter, these Earth-centric definitions become increasingly inadequate. To truly understand life's potential throughout the cosmos, we must re-examine our most basic assumptions about what constitutes a living system. Biology on Earth demonstrates remarkable diversity, from heat-loving archaea in hydrothermal vents to cold-adapted bacteria in Antarctic ice, from anaerobic microbes in oxygen-free sediments to radiation-resistant organisms thriving in nuclear reactors. Yet beneath this diversity lies a striking uniformity of fundamental biochemistry. All known Earth life uses the same genetic code, the same chirality of amino acids, the same core metabolic pathways, and the same basic cellular structures. This uniformity strongly suggests a common origin. All Earth organisms descend from a single ancestral population that emerged billions of years ago. But what if life had originated independently elsewhere, under different conditions? Would it necessarily use the same chemical foundations? Or might alien biology operate according to fundamentally different principles, adapted to environments unlike anything on Earth? These questions lie at the heart of astrobiology, challenging us to distinguish between the universal requirements for life and the particular path taken by Earth's biosphere. Carbon's central role in Earth biology stems from its remarkable chemical versatility. With 4 valence electrons, carbon atoms can form stable bonds with multiple partners, creating the complex, information-rich molecules necessary for life's processes. This ability to form long chains and rings with diverse functional groups makes carbon exceptionally well suited as a backbone for biochemistry, but is it the only possibility? Silicon, directly below carbon in the periodic table, shares many of carbon's chemical properties, including the ability to form 4 bonds. Silicon-based compounds could theoretically support complex molecular structures analogous to carbon-based biochemistry. However, silicon bonds tend to be less stable than their carbon counterparts, particularly in the presence of oxygen, where they readily form silicon dioxide, essentially quartz. A stable but chemically inert compound, unsuitable for the dynamic chemistry of life. Despite these limitations, silicon might serve as a basis for biochemistry under certain exotic conditions. In oxygen-poor environments with different temperature regimes than Earth's surface, silicon chemistry might offer sufficient complexity for lifelike systems to emerge. Some astrobiologists have suggested that silicon-based life might exist in liquid methane or liquid nitrogen environments, where low temperatures would slow reaction rates, but potentially allow for stable silicon compounds that would break down in warmer conditions. The McMurdo dry valleys of Antarctica offer a tantalizing hint of this possibility. Within these seemingly lifeless regions, researchers have discovered microbial communities that metabolize silicon compounds rather than carbon-based molecules. While these organisms still use carbon for their basic structure, their ability to extract energy from silicon chemistry demonstrates that alternative metabolic strategies can evolve even on Earth when conditions demand it. Beyond carbon and silicon, other elements offer additional possibilities. Boron, with its ability to form stable compounds including multiple bonds, has been suggested as another potential foundation for alien biochemistry. Nitrogen-phosphorus combinations could potentially create complex molecules with properties suitable for information storage and structural roles. Even sulfur, which forms diverse compounds and serves important roles in Earth biochemistry, could potentially play a more central role in alien biomolecules. The choice of solvent represents another crucial variable in potential alien biochemistries. Water serves as the medium for Earth's biology for excellent reasons. It dissolves a wide range of compounds, remains liquid across a relatively wide temperature range, has high heat capacity that buffers temperature changes, and participates actively in many biochemical reactions. Yet water also imposes constraints. It breaks down certain bond types through hydrolysis and freezes in a way that expands rather than contracts, creating challenges for organisms in sub-zero environments. Alternative solvents might offer advantages for life in environments unlike Earth's. Ammonia remains liquid at temperatures far below water's freezing point, potentially supporting life on frigid worlds where water would exist only as ice. Liquid methane and ethane, as found on Saturn's moon Titan, could serve as solvents for non-polar molecules unsuitable for water-based chemistry. Even more exotic options include liquid nitrogen, hydrogen fluoride, or hydrogen sulfide, each creating a different chemical environment with unique constraints and opportunities for potential biochemistry. The temperature ranges supported by these alternative solvents differ dramatically from water's liquid range. Ammonia remains liquid between -78 and -33 degrees Celsius at Earth atmospheric pressure, while methane liquefies only below -182 degrees Celsius. At these low temperatures, chemical reactions would proceed much more slowly than in water at Earth's surface temperatures, potentially resulting in metabolisms and lifespans operating on timescales dramatically different from Earth life. These alternative biochemistries would not simply substitute one element or solvent for another while maintaining the same overall structure as Earth life. Rather, they would likely represent fundamentally different approaches to life's essential functions: energy processing, information storage, and reproduction. Different chemical foundations would create different evolutionary pathways, potentially leading to organisms with structural and functional properties unlike anything in Earth's biosphere. Consider how different solvents might influence membrane structure. Earth cells use phospholipid bilayers, molecules with hydrophilic heads and hydrophobic tails that spontaneously form stable barriers in water. In a methane or hydrocarbon solvent, This arrangement would need to be reversed, with hydrophilic portions facing inward and hydrophobic regions interfacing with the external environment. Alternatively, entirely different molecular structures might serve the containment function of membranes in exotic solvents. Information storage presents another fundamental challenge for alternative biochemistries. DNA and RNA serve this function in Earth life through their ability to encode information in sequences of 4 nucleotides, maintained and replicated through complementary base pairing. Alternative genetic molecules would need similar capabilities, stable structures that can store information in a format that allows both replication and the translation of that information into functional molecules like proteins. Several theoretical alternatives to nucleic acids have been proposed, including peptide nucleic acids, PNAs, threose nucleic acids, TNAs, and glycol nucleic acids, GNAs. Laboratory experiments have demonstrated that these molecules can store and transmit genetic information, suggesting that alien life might use similar but distinct chemistry for its genetic systems. Even more exotic possibilities include information storage in patterns of metallic ions, silicon-oxygen frameworks, or crystalline structures that replicate through templated growth. The mechanisms for harvesting and utilizing energy represent yet another variable in potential alien biochemistries. Earth life primarily uses redox chemistry, the transfer of electrons between molecules, to capture energy from light through photosynthesis, or from chemical sources through processes like respiration. These mechanisms rely on the properties of carbon compounds and their interactions with elements like oxygen, nitrogen, and sulfur. Alternative biochemistries might employ different energy harvesting strategies adapted to their environments. In liquid methane oceans, organisms might exploit temperature gradients rather than chemical potentials, using mechanisms similar to thermocouples to generate usable energy from environmental temperature differences. On worlds with intense radiation, life might directly harness high-energy particles through specialized molecular structures that capture and step down this energy to usable forms. In highly magnetized environments, like the surfaces of neutron stars or regions near magnetars, theoretical organisms might utilize magnetic fields directly, perhaps through molecular structures that respond to field fluctuations or gradients. Similarly, in gravitationally extreme environments like the vicinity of black holes or neutron stars, energy might be harvested from gravitational gradients through specialized mechanisms with no analog in Earth biology. The timescales of alien biochemistry might differ dramatically from those familiar on Earth. In conventional water-based systems operating at similar temperatures to Earth's biosphere, basic chemical reactions and biological processes occur on timescales from milliseconds to hours. But in the low-temperature environments of methane oceans or ammonia seas, these same reactions might take days, years, or even centuries to complete. Conversely, in certain high-energy environments like neutron star surfaces, reactions might proceed at rates millions of times faster than on Earth, with organisms potentially living entire life cycles in microseconds. These different temporal scales would fundamentally alter the nature of life processes, from metabolism to reproduction to evolution, creating biospheres operating at rhythms radically different from Earth's. The possibility of shadow biospheres, alternative forms of life existing alongside conventional biology, represents an intriguing extension of these concepts. Some scientists have proposed that Earth itself might host biochemically distinct organisms that remained undiscovered because our detection methods presuppose life with familiar biochemistry. Microorganisms using different genetic codes, mirror image biomolecules, or alternative metabolic pathways might exist in specialized niches like deep crustal environments, yet remain invisible to conventional biological techniques. While no conclusive evidence for shadow biospheres has emerged, the concept illustrates how alternative biochemistries might occupy environments we consider already understood. Similar principles could apply throughout the universe. Planets or moons we might dismiss as uninhabitable based on Earth-centric criteria could host thriving ecosystems based on different chemical foundations adapted to local conditions. The search for such alien biochemistries presents extraordinary challenges. Our detection methods and life identification criteria remain heavily influenced by Earth biology, potentially causing us to overlook signs of exotic life, even if directly observed. When NASA's Viking landers tested Martian soil for biological activity in the 1970s, they used experiments designed to detect Earth-like metabolic processes. If Martian life existed but used fundamentally different biochemistry, these tests might have missed it entirely. This recognition has led to calls for agnostic biosignature approaches that focus on detecting complexity and chemical disequilibrium rather than specific molecules associated with Earth life. For instance, environments containing molecular distributions unlikely to arise through abiotic processes alone might indicate biological activity, regardless of whether the specific molecules resemble those in Earth organisms. Similarly, patterns of energy or resource utilization that create persistent disequilibrium in an environment might signal the presence of lifelike systems, even if their specific biochemistry remains unknown. These broader approaches aim to detect organization and complexity regardless of its particular chemical implementation, making them potentially applicable across the full spectrum of possible biochemistries. The implications of alternative biochemistries extend beyond scientific curiosity to profound philosophical questions about life's nature and distribution throughout the universe. If life can employ multiple chemical foundations adapted to different environmental conditions, then the potential habitats for biology expand dramatically beyond the narrow range suitable for Earth-like organisms. The universe might harbor not just pockets of habitability resembling Earth, but a diverse mosaic of environments, each supporting its own unique form of life. This possibility challenges us to reconsider what we mean by habitability. Rather than defining it as conditions suitable for Earth-like organisms, we might better conceptualize habitability as any environment that allows for the emergence and persistence of complex, self-organizing systems that process energy, maintain internal order, and evolve through selection mechanisms. Under this broader definition, habitability becomes a spectrum rather than a binary property, with environments offering different opportunities for biological or lifelike complexity depending on available energy sources, chemical components, and physical conditions. The implications extend to our search for extraterrestrial intelligence as well. If life can develop along multiple biochemical pathways, then advanced cognition might similarly emerge through diverse mechanisms adapted to different environmental contexts. Intelligence evolving in the methane oceans of a Titan-like world, or in the radiation-rich environment near a neutron star, would likely perceive and interact with the universe in ways fundamentally different from human consciousness. Such alien intelligences might operate on timescales, physical scales, or sensory modalities utterly foreign to our experience. An intelligence adapted to methane chemistry at cryogenic temperatures might process information thousands of times more slowly than human brains, experiencing a single Earth day as subjectively equivalent to decades. Conversely, organisms in high-energy environments might perceive and think at rates making human consciousness seem glacially slow by comparison. Communication with such radically different intelligences would present unprecedented challenges, as their fundamental concepts, cognitive architecture, and sensory experience might share little common ground with our own. Even recognizing their communications as artificial rather than natural phenomena might prove difficult without understanding their native information processing systems and environmental adaptations. These considerations highlight the anthropocentric assumptions inherent in much of our thinking about extraterrestrial life and intelligence. Having evolved within Earth's specific environmental and biochemical context, we naturally generalize from our own experience, assuming that life elsewhere would follow similar patterns and principles. But as we've seen throughout our exploration of life without stars, the universe offers far more possibilities than our Earth-evolved intuitions might suggest. A truly inclusive conception of life would focus not on specific chemical or physical implementations, but on the underlying patterns of complexity and self-organization that characterize living systems. Whether based on carbon in liquid water, silicon in liquid nitrogen, or exotic states of matter in environments we can barely imagine, life represents a fundamental tendency toward localized complexity within a universe otherwise trending toward increasing entropy. This perspective connects to deeper questions about whether life represents an anomaly in an otherwise non-living cosmos, or an expression of principles inherent in the fabric of reality itself. If complex, self-organizing systems can emerge across such diverse environments and biochemistries, perhaps life in its broadest sense represents not an aberration, but an expected outcome of the universe's fundamental properties. Some theoretical physicists have suggested that the laws of physics themselves might favor the emergence of complexity and lifelike organization. Stuart Kauffman's concept of order for free proposes that certain types of complex systems naturally generate order and pattern without external guidance, simply as a consequence of their internal dynamics. Similarly, physicist Lee Smolin has explored whether the universe might have evolved through a process analogous to natural selection, potentially explaining why physical constants appear finely tuned for complexity. While such ideas remain speculative, they highlight a profound possibility that life, broadly conceived as complex self-organization, might be written into the mathematical structure of reality itself. If so, then the emergence of life, albeit perhaps in forms radically different from Earth biology, would be not merely possible but probable throughout the cosmos, arising wherever conditions allow for sufficient complexity to develop and persist. This expansive view transforms our understanding of life from a fragile, improbable phenomenon requiring precise conditions to a robust, versatile expression of underlying principles that can manifest across diverse environments. Earth life, remarkable as it is, would represent not a singular miracle, but one instance of a broader pattern woven into the universe's fundamental nature. As we redefine our conception of life to encompass this broader spectrum of possibilities, we simultaneously expand our vision of where life might exist. Beyond the traditional habitable zones, around sun-like stars, lie countless other environments where different forms of complexity might emerge. From the subsurface oceans of icy moons to the atmospheres of brown dwarfs. From the exotic chemistry of rogue planets to the theoretical realms of dark matter or neutron star crusts. This redefined vision of life and habitability offers a profound shift in perspective. Rather than inhabiting a largely sterile cosmos with occasional oases of habitability narrowly defined by Earth-like parameters, we might exist within a universe teeming with diverse forms of lifelike complexity, most operating according to principles so different from Earth biology that we've barely begun to imagine them. The lack of a star need not mean the absence of life, only the absence of life exactly like our own. As we expand our conception of what life can be, we simultaneously expand our understanding of where it might exist, discovering potential habitats in environments we once dismissed as hostile to biology. The darkness between stars, rather than representing a barren void, might harbor its own unique expressions of cosmic complexity, waiting for us to develop the conceptual frameworks and observational tools to recognize them. Our journey through the possibilities of life without stars ultimately leads us back to a fundamental truth. The universe's creative potential likely exceeds our imagination, shaped as it is by our specific evolutionary and planetary context. By stretching beyond these limitations, by considering biochemistries, environments, and organizational principles unlike anything in our direct experience, we prepare ourselves to recognize whatever forms of complexity the cosmos might have generated through its billions of years of cosmic evolution. As we search for life beyond Earth, this expanded perspective guides us to look not just for familiar biosignatures in familiar environments, but for broader patterns of complexity and organization across the full spectrum of cosmic conditions. Whether we ultimately discover microbes in subsurface oceans of icy moons, exotic chemistries in the atmospheres of rogue planets, or forms of organization so different from Earth life that they challenge our very definition of biology, the journey itself transforms our understanding of life's place in the universe. In the absence of starlight, life may indeed find a way, not as an exact replica of Earth biology, but as novel expressions of the same fundamental drive toward complexity that characterizes our own living world. The lack of a star might not mean the absence of life, but the presence of life, unlike anything we've yet imagined. A testament to the creative potential inherent in a universe governed by principles that seem intrinsically to favor the emergence of order, pattern, and ultimately, perhaps, consciousness itself. As we stand at the frontier of astronomical discovery, humanity's quest to find life beyond Earth has taken us to places we once considered inhospitable. Now, our spacecraft and telescopes reach toward the darkest corners of our solar system and beyond, where no star's light directly touches. The search for starless life represents one of the most fascinating chapters in our exploration of the cosmos. The Europa Clipper mission, set to launch in the coming years, will venture to Jupiter's enigmatic moon Europa, orbiting this distant world with instruments designed to peer beneath its icy crust. The spacecraft will map the moon's surface in unprecedented detail, analyzing its composition through sophisticated spectrometers capable of detecting organic molecules. Most crucially, it will measure the thickness of the ice shell and confirm the presence of subsurface water plumes that occasionally burst through cracks in the surface. These plumes may carry material from the vast ocean below, potentially containing biosignatures of microbial life thriving in complete darkness, warmed only by the moon's internal heat. Simultaneously, missions to Saturn's moon Enceladus are being developed with even more ambitious goals. Already, the Cassini mission has flown directly through the water plumes erupting from Enceladus's south pole, detecting organic compounds and molecular hydrogen, a potential food source for microorganisms. Future missions propose sending landers equipped with drills capable of penetrating the thin ice at the South Pole, potentially providing humanity's first direct contact with an alien ocean. But our technological reach extends far beyond our own solar system. The James Webb Space Telescope, humanity's most powerful eye in space, has revolutionized our understanding of distant worlds. With its infrared capabilities, Webb can detect the chemical signatures in the atmospheres of exoplanets, searching for gases like methane, water vapor, and carbon dioxide that might indicate biological processes. Most exciting is its ability to study planets orbiting dim red dwarf stars and even brown dwarfs, those failed stars too small to sustain nuclear fusion. Already, Webb has examined systems like TRAPPIST-1, where 7 Earth-sized planets orbit a tiny star, finding tantalizing hints of atmospheres that could potentially harbor life. Perhaps most revolutionary is Webb's ability to study rogue planets, worlds drifting through interstellar space without a parent star. By capturing the faint infrared glow these planets emit from their internal heat, astronomers have detected water vapor and complex molecules in their atmospheres. These discoveries suggest that even without starlight, these nomadic worlds might maintain warm interiors and potentially habitable conditions beneath their frozen surfaces. The next generation of space telescopes promises even greater capabilities. The Habitable Worlds Observatory, currently in development, will directly image Earth-like planets around Sun-like stars, but its technical capabilities might also allow it to study the large moons of gas giants in distant solar systems, places where starless life might exist in subsurface oceans. Ground-based observatories are contributing to this search as well. The extremely large telescope, with its 40-meter primary mirror, will collect enough light to analyze the atmospheres of smaller and more distant worlds than ever before. Its adaptive optics systems will correct for atmospheric distortion, allowing it to potentially detect biosignatures around brown dwarfs and even study the surfaces of the larger rogue planets within 100 light-years of Earth. Meanwhile, gravitational lensing missions represent our most ambitious plans to observe distant worlds. These missions would send spacecraft to the solar gravitational lens point, 550 astronomical units from the Sun, where our star's gravity bends light like a massive lens. From this vantage point, theoretical calculations suggest we could image the surface features of exoplanets in extraordinary detail, potentially revealing continents, oceans, or even signs of advanced civilizations on worlds both with and without stars. Radio astronomers continue their patient search as well, scanning the cosmos for technosignatures, artificial radio signals that might indicate intelligent life. Recent advances in machine learning have dramatically improved our ability to sift through the cosmic noise, identifying patterns that might otherwise go unnoticed. Some astronomers now specifically target regions where rogue planets are suspected to cluster, considering the possibility that advanced civilizations might inhabit engineered habitats on starless worlds. Closer to home, NASA's Dragonfly mission will soar through the thick atmosphere of Saturn's moon Titan in the coming decade. While Titan receives minimal sunlight, its thick atmosphere and hydrocarbon lakes make it a prime candidate for exploring bizarre forms of life that might utilize different biochemistry than Earth's. The rotorcraft will sample the surface at multiple locations, analyzing the complex organic chemistry of this frigid world. Interstellar probes, too, are no longer mere science fiction. The Breakthrough Starshot initiative continues its development of tiny light-sail spacecraft that could be accelerated to 20% the speed of light using powerful ground-based lasers. Such probes could reach nearby star systems within decades rather than millennia, potentially visiting rogue planets encountered along the way and transmitting data about these mysterious wanderers. The search extends beyond conventional planets and moons. Astronomers now regularly monitor the Oort Cloud and Kuiper Belt objects in our solar system using infrared telescopes. These observations have revealed unexpected activity and thermal signatures suggesting that even at the frigid edge of our solar system, internal heat sources might create pockets where simple life could potentially exist. Perhaps most profound are the changes in our search methodology. Scientists have developed new biosignature frameworks that don't rely on assumptions about photosynthesis or oxygen-based biochemistry. Instead, they look for chemical disequilibrium of any kind, imbalances that suggest biological processes might be at work. This paradigm shift allows us to search for life in environments where energy comes not from a distant star, but from chemical reactions, radioactive decay, or tidal heating. Advanced computer models now simulate the potential for life in these extreme environments, calculating the energy available from various non-stellar sources and the forms life might take to harness it. These models suggest that in some subsurface oceans, chemical energy might be abundant enough to support ecosystems as complex as Earth's deep-sea hydrothermal vent communities. As our search continues, one thing becomes increasingly clear: the cosmos is stranger and more varied than we ever imagined. The dark, starless regions between and beyond the light may not be as lifeless as we once assumed. In the absence of a star's warming rays, life may still find a way, drawing energy from sources we're only beginning to understand. And as our instruments grow more sensitive and our missions more ambitious, we come ever closer to answering one of humanity's most profound questions: are we alone in this vast and varied universe? Throughout our cosmic journey, we've ventured beyond the warm glow of stars to explore the possibility of life existing in darkness. As we bring our exploration to a close, we're left with a profound appreciation for life's potential resilience and adaptability, traits that may extend far beyond the boundaries of our sun-kissed world. Life on Earth has repeatedly astonished us with its tenacity. From the scalding depths of hydrothermal vents to the frozen wastelands of Antarctica, from acidic hot springs to radioactive environments, living organisms have colonized nearly every conceivable niche on our planet. This remarkable adaptability suggests something fundamental about life itself. It finds a way, often defying our expectations of what's possible. Consider the creatures dwelling in Earth's deepest oceanic trenches, where pressure would crush most organisms and eternal darkness prevails. These resilient beings have evolved to thrive without sunlight, drawing energy from chemicals seeping from the planet's interior. They represent not just curiosities of evolution, but windows into how life might function throughout the cosmos in starless environments. If life can flourish 11 kilometers beneath our oceans, why not beneath the ice of Europa or Enceladus, warmed by tidal forces rather than sunlight? The universe, in its vastness, presents infinitely more possibilities than constraints. For every Earth-like planet circling a sun-like star, there exist countless other environments. Rogue planets drifting through interstellar space, moons orbiting gas giants far from their host stars, brown dwarfs emitting only faint infrared light, and worlds we've yet to imagine. Each offers unique conditions that might nurture novel forms of life. Our search for life beyond Earth has traditionally focused on finding conditions similar to those that support life here: liquid water, moderate temperatures, and available energy sources. But perhaps this approach reflects our limited imagination rather than cosmic reality. The chemistry of carbon offers billions of possible molecular combinations, and we've explored only a fraction of these possibilities. Silicon, with its similar bonding properties, could potentially form the backbone of entirely different biological systems. Even more exotic alternatives might exist: life based on ammonia rather than water, organisms that metabolize methane, or biological processes that function at temperatures approaching absolute zero. The concept of shadow biospheres reminds us that even on Earth, we might be overlooking entire ecosystems operating on different biochemical principles. If multiple forms of life could evolve independently on our own planet, the possibilities across the universe become truly boundless. Perhaps life doesn't require the specific conditions we've assumed are necessary. Perhaps it requires only sufficient complexity and energy flow, resources that might be available in environments vastly different from our own. The philosophical implications of finding life in starless environments would be profound. Such a discovery would force us to reconsider our place in the cosmos and expand our understanding of what it means to be alive. If life can emerge and persist in the darkness between stars or beneath the ice of frozen worlds, then the universe may be teeming with diverse forms of life, each adapted to its unique circumstances. The cosmic story of life would not be a rare occurrence centered around stars like our Sun, but a universal phenomenon expressing itself in countless variations across space and time. This broader perspective on life's possibilities also changes how we think about our own existence. Earth is not simply a perfect cradle for life, exquisitely tuned to our needs. Rather, life on Earth has continuously adapted to changing conditions, evolving new forms and functions in response to challenges. This adaptability, not perfect initial conditions, may be life's most essential characteristic and its greatest strength. As we look to the future of space exploration, the search for starless life will undoubtedly expand. New telescopes will peer further into the cosmic darkness, detecting rogue planets and studying their properties. Spacecraft will venture to the icy moons of our solar system, perhaps one day drilling through their frozen crusts to sample the waters below. Advanced observatories will analyze the atmospheres of distant worlds, searching for chemical signatures that might indicate biological processes operating without the benefit of starlight. These explorations will be guided not just by scientific curiosity, but by a deepening appreciation for life's inventiveness. Each new environment we study offers another opportunity to discover how biology might solve the challenge of existence. The dark, cold regions between and beyond stars are not simply voids to be traversed, but frontiers to be explored, each potentially harboring life forms as yet unimagined. Consider the possibility that somewhere in the cosmos, organisms metabolize radiation directly, converting it to chemical energy, much as plants convert sunlight, or life forms that harness the gravitational energy of a black hole's accretion disk, evolving in an environment utterly alien to our experience. or beings that drift through interstellar clouds, extracting energy from cosmic rays and chemical gradients over timescales of millions of years. Such possibilities may seem fantastic, but they remain within the realm of physical possibility. And the universe has repeatedly demonstrated its capacity to surprise us. Even if we never discover such exotic life forms, the search itself enriches our understanding of cosmic processes and our place within them. By questioning our assumptions about what life requires, we develop a more nuanced appreciation for the conditions that enabled our own existence. We recognize Earth not as the only possible cradle for life, but as one expression of a universal potential, a potential that may manifest wherever sufficient energy and complexity coincide. The true wonder of our cosmic journey lies not just in what we might discover, but in how those discoveries transform our perspective. Each new finding reminds us that we are part of something greater, a universe of infinite possibility, expressing itself through stars and planets, through chemistry and biology, through consciousness and curiosity. In seeking life beyond the light of stars, we ultimately learn more about ourselves and our connection to the cosmos that birthed us. As we gaze at the night sky, we now see the darkness between stars not as empty void, but as fertile ground for possibility. Those seemingly barren regions may harbor worlds drifting in eternal night, yet perhaps warmed from within and nurturing their own unique expressions of life. The stars themselves, once thought essential for life, may be just one of many cosmic energy sources capable of sustaining biological processes. This broader vision of life's potential transforms our understanding of the universe itself. No longer a vast emptiness punctuated by isolated islands of habitability, the cosmos becomes a tapestry of interconnected possibilities, each environment offering different pathways for complexity to emerge. In this view, life is not an accident or a rarity, but an expression of the universe's intrinsic creativity, a natural outgrowth of physical laws operating across billions of years and trillions of environments. Our journey of discovery has only begun. Each new telescope, each space mission, each laboratory experiment expands our understanding of what's possible. The coming decades promise revelations that will challenge our assumptions and inspire new questions. Perhaps we will find microbial ecosystems beneath the ice of Europa, or detect biosignatures in the atmosphere of a rogue planet, or discover an entirely new form of complex chemistry operating in the clouds of a brown dwarf. Whatever we find, we can be certain that the universe will continue to surprise us. Just as life on Earth has repeatedly transgressed the boundaries of what we thought possible, life beyond Earth, with or without the benefit of starlight, will likely defy our expectations. And in that defiance lies the greatest wonder of all, the infinite adaptability of life and the boundless creativity of the cosmos that nurtures it. As our exploration comes to a close, we're left not with definitive answers, but with a universe of possibilities far richer than we imagined. The darkness between stars may not be empty after all, but filled with worlds harboring their own unique stories. Stories we are only beginning to read. In the absence of starlight, life may still find a way, drawing on the universe's abundant energy sources and expressing itself in forms we have yet to discover. The search continues, guided by curiosity and wonder, as we reach ever further into the cosmic night.